Alô, alô, teste.
So let's get started. Hello everybody, welcome to the second day of Phosphorus. Yeah, yesterday was a nice day, right? Very intense day, lots of presentations, good talks, good discussions. I really enjoyed that. So hopefully to have another good day today. Some people asked me, where are the dev rooms? So if you are following us since the beginning, the proposal for Phosphorus was to have talks, what we're having here today, but also one or more dev rooms, or mini conferences, sometimes called mini conferences, right? Separate groups discussing specific technologies, doing development, or maybe, even patching a project or some kind. It's very open what you do in a dev room. It depends on what the groups wants to do. But in the end, we haven't received any proposals. So that's why we don't have dev rooms this year. Hopefully next year we will have some. I believe dev rooms are very useful. So I really hope that for next year we have some proposals. As I said before, 10 years ago in the upstream, we also had talks and dev rooms. It was great. The dev rooms were very interesting, even though at that point in time, we didn't receive many proposals. We received, I think, 2 or 3 proposals. And I organized one of the dev rooms, and it was quite great. It was about virtualization at that point in time. We had very good discussions. The problem this time is that I wasn't able to organize a dev room and the conference at the same time as I did last time. So it was quite crazy 10 years ago. And now 10 years older, it would be even more crazy. So, I thought that someone would like to propose dev rooms. That didn't happen, so that's why we don't have dev rooms this year. Just crickets, right? But hopefully next year. Let's see. I'll talk a little bit of, the same things that I talked yesterday. So if you were here yesterday, you heard probably the majority of the stuff that I'm going to say. So we don't have a code of conduct. However, Brazilian laws already cover, we think at least that Brazilian laws already cover a number of these things. So we are not going to support any kind of harassment, discrimination, or, any kind of behavior that is not enjoyable by others. If you have any issues about that, just come and talk to me and Rafael, and we will take any needed actions. Data privacy, the same as I said yesterday as well. We will not share your information except, as I said yesterday, we want to share your emails with some of our sponsors because they requested that. So for next year, we will be more intelligent on that aspect and ask during the registration if you want to share your information or not. But this time, if you don't want us to share your email with the sponsors, just come and tell us, and we are not going to do that. At the same time, we are taking photos during the conference, and we had some photos as well on the get-together last evening, which was great as well. So if you don't want to appear in the photos, just let us know, and we will remove you from the photos. There is nice artificial intelligence these days that can remove people from photos, right? So I also want to thank again our sponsors, Husk and Red Hat, Institute of Computing and Unicamp. They provided a space for us to have these sessions. They are providing the nice infrastructure to do the streaming as well. We had 140 visualizations in the streaming yesterday, which is quite great.
170.
170, so it's even more than I thought. So that was really great. I mean, it seems that we have some attention at least, right, for the first time of this conference. There is Risk 5. I have to say their names today, so Rafael is not here. Risk 5 is also supporting our efforts. Rafael works for Risk 5. They have been an important partner. Leonardo, I work for Leonardo. They are also supporting the conference. And ICTL, I'll talk a little bit about them afterwards, but they have been supporting us with funding and legal aspects, organization, that kind of stuff. So Husky is a fintech that makes international transfers easy for Brazilians, especially for tech professionals working for companies abroad, right? Which is my case, by the way. I use their services. So they have been founded in 2016, offering a seamless, hassle-free payment solution for users and their employers. And last year they were acquired by Nomad, which is really a fintech providing global account and services in the finance system around the world. Red Hat, I mean, Red Hat has been around for a long time, 20 something years, right? 25 years, I think, or even more, 1997, if I recall correctly. They were Anyway, they are the leading provider of enterprise solutions in open source ecosystems. They have a broad portfolio of products. I'm pretty sure that everybody here at some point in time, they use the product from Red Hat. Instituto para a Conservação de Tecnologias Livres is a non-profit organization that exists in Brazil. They are basically providing the kind of services that we need when we are organizing conferences such as this one. So nor Rafael nor me, we don't have a company. It's quite difficult to have sponsors if you don't have a legal representation. They want to pay this for a company or a non-profit. They want to have a legal face in front of the conference. So that's the kind of service that ICTL provides. They can help us to receive donations, sponsorships. They can pay for contracts, they can sign stuff. So it's really good, and they can maintain our funding as well. They have a number of projects. So they have organized DebConf 19, which was in Curitiba, and they are now a supporter of FOSForums as well, right? I want to thank again the people that help us here. So Rafael, Luciano and Iago, they are our volunteers here today. They are helping with everything we need. Professor Rodolfo was the one that intermediated all the negotiations with Unicamp and the Institute of Computing to get this room allocated for us today. Gabriel gave me a number of insights. He was helping the organization of Linux Dev BR with their infrastructure. Guilherme was basically my beta tester. And Gustavo Padovan and Bruno Gili, they also organized Linux Dev BR and helped us with funding and some legal aspects as well. They connected us with Antonio and Daniel from ICTL, and Renato Bolin, as I said yesterday, is a guy that helped organizing Euro LLVM and FOSDEM a number of times. He provided us a number of insights. And last but not least, Tadeu Cascardo helped us with, inspiration, basically. I mean, he has been an active voice in free and open source movements in Brazil for a long time. We will have lunch break, and the same restaurant that was opened yesterday is going to be open today. So they have, they usually don't open in the weekend, but we were able to get some exception with them. And they will be open today as well. And hopefully, even though it's quite expensive, they will provide some amount of coffee to us. But let's see. Rafael was negotiating that right now, so let's see if that is going to work. Our agenda for today. So we will have a hardware-focused morning. So we have a session building the future accelerating digital design with open source CDA tools by Rafael. Then we have an introduction to Risk 5 with Mikhail. Is that correct, Mikhail? Mikhail. And then we have a lightning talk by Eduardo on IoT architecture in TinyML era. I don't know exactly what is Eduardo is going to talk here, but I am quite interested in this one because TinyML was something that I crossed the path while working at Linaro. And it's quite interesting what these guys are capable of doing with very tiny devices and machine learning. Then we have a talk by Luke. Pedro is not going to be available here today on Malloc Adventures. I fixed this in the schedule, the live schedule in the internet, but I didn't update the slides, so it's just Luke talking about some work that they are doing here in LK Camp, if I understand correctly, on Malloc. Oh, this is after lunch, by the way, right? So we have lunch here. You can see. At 2 p.m. we are going to get back. Lunch will be more or less the same time as yesterday, so we will probably wrap up for the morning around 12:15, 12:20, and then we get back at 2. We have then a talk by Jadila and Pablo on Debian image generations for single board computers using Devils, controlling packages and files. We will have a coffee break without coffee probably in the afternoon because I doubt the restaurant will provide coffee for us, late afternoon in a Sunday. But anyway, and stateless decoders and then the new AVI1 kernel macro API by Daniel at 4 p.m. And last but not least, our last talk for the day is about Bitcoin, open source development and how it works. Hopefully you all will enjoy the day today. I am quite excited to stay here and watch what our presenters have to show to us today. So what's next? I mean, some people ask me about that, and I would like to give this as a spoiler right now. We are already planning the event for next year. We have coffee. Yeah, I said that he was looking for that, right? So I think I won't spend all the 30 minutes here, so you will have time to get some coffee before the first presentation. But anyway, let me get back to what I was talking before. We are planning to do this conference next year already. And it will happen in the last weekend of August, just as this year, right? So we are trying to set this date as the date for this conference. So just to give you a heads up in case you enjoyed as much as I did, and in case you are you start to plan what you're going to do in August, late August next year, right? And that's it. Thank you very much. I hope everybody has a great day. Is there a question over there?
Yeah, no, just a comment. It could be interesting to have a forum, like a discourse forum for this community, so that we can be in contact throughout the year.
Yeah, some people ask me about that. I have some mixed feelings about that, but I can definitely create one at some messaging tool. The reason why I have some mixed feelings, and I can say that openly, I mean, Linux Dev BR used to have a channel in Telegram, right? It wasn't very active, and in practice, nobody really used that to communicate. So, if it's not going to be useful, I don't want to create yet another channel. But yeah, I can try, and we see from there. I'll do that. I mean, let's just I'll do that and send an email with a channel somewhere, probably in Telegram, because I think this is the one that has less resistance. Maybe, I don't know.
Think about something in the web, like discourse.
Oh, okay, yeah, that's a good idea. Yeah, let's talk afterwards, and we can definitely set something up. I can invite everybody, and whoever wants to join can join. Okay. Any other questions, comments? All right, so let's grab some coffee before the next presentation that starts in 13 minutes. Thank you very much.
So, good morning. My name is Rafael Oliveira, and today I'm talking a little bit about using EDA tools, open source EDA tools, which stands for Electronic Design Automation Tools, in digital design. So, a little bit about me. I am an undergraduate student at Federal University of Santa Catarina. Currently, I'm working at Tipus Microelectronics as a digital IC designer. I'm also researching in the embedded computing lab in the same university I'm studying. I'm finishing my graduation thesis there. I'm also founder of VLSI Brasil, which is a blog where I try to share some knowledge and tips about digital design. And I'm founder of Osiris, which is a research group focused on RISC-V microarchitectures. I'll talk a little bit more later. So today I hope to share with you guys a little bit about my experience in the digital IC design field. Well, the agenda for today, I will start talking more about the semiconductor industry in the world and in Brazil. I'll make some distinctions about some nomenclatures that we have in the industry. I'll talk about digital design, EDA tools, and I'll finish going step by step in a digital IC design flow that usually we can use to design our chips or microchips. So starting talking about the semiconductor industry, to keep simplicity, I'll just subdivide in two main groups of companies that we have in the industry. The first one are companies that make the design. They have a specification of the architecture that the client have or the product that they are building. So they go through a lot of steps to have a file or a bunch of files that describe the geometric format of all the device that must you have in the chip after manufacture. And we also have companies that will bring those specifications through reality manufacturing the chips and send it to the clients or the company to make a lot of tests. We also can merge those type of companies together. I know in the industry we have a bunch more companies that make the silicon ingots or the companies that build the tools for designers to use or other companies that build the machines to manufacture the chips. But as I said, just to keep simplicity, I'll focus on those two groups that will give some base for my presentation today. We also can merge those companies and subdivide it into IDM companies, which are companies that make the design of the microchip, but they also have facilities to build their own chips. And here we have some examples, for example, Texas Instruments or many others, just a few examples. We also have companies that we call fabless. They have not facilities to build the chips, they only make the design. And here is the company I work, Chips Microelectronics. We just make the design, send to other companies to manufacture the chips. We can perform some tests, but we don't have that complex machines to build the chips. So those companies enters on this group of fabless companies. And we also have pure play companies. They are very specialized into building the chips. So I can have my company or work for a company that make the design and send for those companies to manufacture the chip. They are responsible not only for manufacturing, but for giving to design companies a lot of files and rules that can manufacture the chips. So if we follow those rules, they are able to manufacture our chips on their technologies. Of course, I'm just making things simple here. Some of those companies can also design chips, but it's not their principal business, you know. So I divided those companies on those three categories. But where Brazil are on this industry? We also have a semiconductor industry here in the country. If we see a report for a few years ago, we brought some revenue to the country in the industry. Of course, when we look into the global market, we are just a small representation of that, less than 1%. So we are a small industry here, but we have jobs, we have opportunities to work in the semiconductor in the country. We also have some government support to grow the industry here in the country. We saw a few years ago in the chip shortage. After that, a lot of governments investing huge amount of monies to manufacture their own chips inside their own countries to depend even less on other countries to provide their own chips for their industry. So it's very good to see Brazil also investing on the country and on this field. Well, here are some examples of companies that we have here. I didn't put all of them, there are a few more, but companies specialize on manufacturing and packaging memories. We also have some companies that design the microchips or the ASICs. And again, we have the industry, we have opportunities to work designing hardware. And maybe on this presentation, I can instigate you guys to take a look on hardware design too, because we have opportunities in Brazil. So let's go make some distinctions, and I'm sure that most of you guys are very familiar with some of these nomenclature. For example, FPGAs, which extends for Field Program Gate Array, are microchips that after manufactured, we can make the chip perform some tasks, but if we want to change that, I just write a Verilog or VHDL code, a hardware description language, I send to that, and then the chip can rebuild its internal connections, not physically, but he can reallocate the logic blocks that they have and perform other tasks. Those microchips are very versatile. I can put in a product or in a other platform that I'm using. But if I want to change that, those tasks that the chip is performing, I can do that very easily. Of course, they don't have the best performance in area or power. They can lack on that. So we can build an ASIC, which extends for application-specific integrated circuit. They are more specialized in doing a bunch of tasks. After manufacturer cannot change it, we can use just part of those tasks or those functionalities, but they can be very specialized or very custom-made in power management or area, and they can cost a little more to manufacture, but after that I can integrate with my application easily and have a very specialized chip for my product or for my application. And we also can have IPs, which extend for intellectual properties. Those are logic units that I can integrate in my ASIC, or I can sell them as a product for other companies to integrate it with their solutions. For example, here I brought two ideas. For example, memory controller. I can have an ASIC that has a memory, and I use this IP to control my memory, but I can sell also a memory controller to other companies that are working with similar technology of memories, and they can use my memory controller. So there are other kind of chips, but just to make an illusion what we can work here and what a design company or you can design with EDA tools. But what those chips have in common? And here we come to a transistor. And I'm also aware that most of you guys are familiar with transistor. What is it? It's basically a switch, and I can turn on and turn off this simple switch. And with that, I can create Boolean logic, and I can have more complex computational based on this simple switch. Of course, this is not the only one electronic device. We have others, but for digital design, we rely most of the time on this type of electronic device. And since its creation in 1947, we have a lot of new families and new type of transistor that was developed along the time, always trying to improve power management or reducing area. So a lot of new technologies was developed based on a lot of research. We started with planar MOSFETs. We then became working with FinFETs, and the actual state of the art, we are working with gate all around, which are nanowires or nanosheets. And just to make a distinction between here, if we compare a technology basically 10 years old almost for 14 nanometers, it was close to 6,000 smaller than a strand of human hair, which is very, very small. And if we compare a human DNA, it's just 5 times bigger than a human DNA. And this is a technology of 10 years old. Nowadays, we hear the news and industries manufacturing 3 nanometers. So we are getting very, very, very small and very, very complex to design a microchip using advanced technologies. But only a transistor cannot do much. We have a very controllable switch, but with only one switch, we cannot do anything very, very complex. But if we start combining those switches in a very smart way, we can start building logic gates. And here we can have more complex operations in our microchips, but also it's not enough to build a complex computer or a complex chip. But if we start combining those logic gates, we can achieve digital circuits. And if we combine digital circuits with analog circuits, we can become building ASICs. Of course, every time I'm going to build my microchip, it's not very productive. I start building my own transistor, then building my own logic gates, and then my own digital circuits, and then my ASIC. It's not very productive. We can do that. We can do some custom logic gates or custom transistors. Not really transistors, but we can build some custom-made, but it's not very smart to do that. So we rely on PDKs, which stands for Process Design Kit. Remember that companies that I told that manufacture the chips, they are responsible for providing some files and some rules for us designers. So generally they pre-built some logic gate, the design, the logic, the schematic, and they provide to companies to use that. And they say, if you use our logic gates, if you follow our rules, I can guarantee you that I'll be able to manufacture your chip with a very high yield. So it shortcut the process of designing a microchip for us designers. So we rely on that. So what we can do? We can make a hardware description language, designing the behavior or the function of the circuit that we are trying to build. Then we map to those pre-built standard cells that the founder provide us, and we can achieve our design. Of course, this is not very easy to do, and if we look into those advanced technology of 14 nanometers, we cannot do that manually. It will be impossible to connect millions or hundreds or thousands of logic gates. Would be very, very difficult to do that manually. So we rely on EDA tools, which I already stated that it stands for Electronic Design Automation Tools. There are a lot of companies that, not so much, but design those softwares. They are very complex. They have very complex algorithms interns to automate the process of designing a microchip. They are very expensive to get the license to use because most of them are proprietary. So for us researchers or for us common people, if we don't have a company with a lot of money to buy those licenses, it's very difficult to get access. They are also not very, if you want to make a custom, some custom designs in the tool, sometimes you don't have that flexibility because you don't have access to the algorithms. So we rely on open source EDA tools. And later in the last 10 years, maybe there are a lot of initiatives on open source tools for designers, and it has made possible to allow us to download those tools. We have access to all the source code, and we can use them to design, or we can use them to make some customizations in the code for perform some tasks that we want in our process of designing a microchip. Here are some examples of tools. For example, Yosys is the state-of-the-art of open source tools to make logic synthesis. I'll talk a little bit later in more detail about those tools. But we also have EDKs, which we call electronic educational design kits. Those technologies are here out there for all of us to use to design our microchips, but those technologies are only for educational purpose because they cannot be manufactured. But there are similar specifications about what we use in the industry, and we can use to make some research to learn more about digital design or circuit design using those EDKs. But we also have some open source PDKs. And here a few of them. The Skywater 130 nanometers, one from Global Foundries, and more recently, one from IHP. So we have all the tools and the files that we need to design our own microchips. And those open source PDKs, we have some companies that are doing some open shuttle. So we also have the opportunities not only for designing our microchips, but send them for manufacturing and getting back our own microchips. It's very good to see the community moving and taking actions to make the process of designing hardware more accessible for all of us. But if we take a look here, well, 110 nanometer, it's very far from the latest technology of 3 nanometers or 14 nanometers. Yeah, those are very mature nodes that we call, that are around the market for like 20 years. But if you are not designing the latest microchip to go to the latest smartphone, this is enough to make most of the applications, IoT applications, or for the automotive market and many other applications. It's enough sensors, enough to use the technologies like that are around for like 20 years and are big nodes if we compare with the latest one. It's not big because 110 nanometers is very small, but it's very useful for most of the applications that we have nowadays. Well, I gave some highlights about the industry, what we need to build our own microchip. So now I'm going a little bit more about the flow and the steps that usually we designers use to take from a specification to a file that we can send to the foundry to manufacture our own chips. Well, the first step is getting with our RTL code. So what we do here, we don't need any special tool or EDA tool to do that. If we have an text editor, we can write some Verilog or VHDL or any other hardware description language. In this step, we make an abstraction of our design or of our architecture. And we also describe some test bed that we can extract our design to check if we design everything okay, if it's okay with our architecture or the specification that we got from the client. Well, if we build more complex test bed, I can validate more of the inputs of our design, but of course it's not possible to make a test bench that cover everything, because if I have a more complex design, it will be impossible to make 100 million of vectors to test all the input combinations. But we also want to make test benches that will cover as much as we can for our design to validate it. So usually we work with a margin of error that we can say, okay, I test enough of our design, so I guarantee that it will perform the tasks I need. So we have our description of the behavior of our design, we have our test bench, so we need tools to apply those test benches into the design to check if we did everything okay. So here we rely on Icarus Verilog. I'm giving here an example using Verilog, because I do prefer Verilog over VHDL. It's easier to work and more flexible, but you can take a look on other tools to compile your hardware description language. So we use Icarus Verilog, it's a Verilog compiler, and we also use GTK Wave, so we can see and debug the waveform that we created. Here a simple example. So in this stage, we apply our test bench to our design using the Icarus Verilog tool. So it will test all the inputs. We can write some displays to check if the test was okay. But we also can make some conversion and see how much our test bench are covering for our design. So here we have another tool called MCY. It's a tool that comes with the package of IOSIS, which is, I'll talk a little bit more later. So MCY, we can create a lot of mutations. So those mutations are applied to our design, and then it checks if the test bench got those mutations. So it inserts some failures in the design, and we'll check if the test bench are getting that, and it can give give us a report, and a visible one in a very nice dashboard, so we can see, okay, my test bench is covering enough of my design, 85% or 9%, so I can check that with MCY. Of course, we can take simulations later. This is the first step. I did simulation in the RTL code that I have, but after I make synthesis, after I map my design into the technology I'm going to manufacture my chip, I can make simulation again to check if everything is okay and if the tool didn't change the behavior of the design, and I can do that later after I finish the layout. So this is not a linear process of designing. Sometimes I need to go back and make a step that I already did because I did some modifications in my design. I'm presented here in a linear path, but always we are going later and back until we have a design that are good. So I did my behavior description, I make the test bench, I test, everything is okay, it's well covered. So I need to map my design into the technology I'm going to manufacture the chip. And as I already said, here we have IOSIS. IOSIS is an open source tool, and this tool is responsible for mapping my behavioral description into a technology that I'm going to use. And here I have an example of what is this mapping do, or this translation, because now I'm not going to have anymore behavior description. I'll have a gate level netlist, which means the behavior of my design will be translated of a bunch of logic gates, simple logic gates, that connected will perform the same behavior or the function I described later. So from now, all the steps are technology based. So from here, I'm already set which technology I'm using, because I already sent to the tool, I'm using this PDK from this foundry. So map everything here based on that. This stage also makes some logical optimizations. Here is a visual example of synthesis made by IOSIS. So it will take less logic gates that will be able to perform the task I'm trying to model, and it will respect the timing constraints that I sent to the tool too. And also it will make the logical connections between those logic gates. And we will see later that why it makes those logical connections and map that very good, because later we are going to translate those logical connections between the logic gates into physical connections, and it will be creating wires between the gates when we started to make the physical design.
So, Rafael, just to make sure I understood, I mean, so IOSIS, for instance, you are going to provide the Verilog or VHDL and the PDK.
Yeah, not all the PDK. There is a file that we call Liberty file, and this map the technology, all the logic gates that have in the PDK, but it will also map the timing constraints of every logic gate and how much time they have in the transition of the gate from input to output. So IOSIS will synthesize it based on that file. So we.
Right, and everybody uses this file. I mean, is this some kind of standard?
Yeah, it's a standard. Even the proprietary tools use the same file.
Okay.
Yeah. So the open source tools are very related with the proprietary ones. Okay, so it performs the optimizations and also the logical connection that later will be translated into physical connections. Well, after that, we must check if our design doesn't change, if the tool didn't make some modifications in our design. So we make some logic equivalent check. And here again, we have another tool inside the OSIS, which we call EQI, and it will perform some formal equivalence check. So we send to the tool our golden design, which is our RTL that we already make some test bench and check that it was working okay. And we also pass our gate level netlist, and it will compare, it will make some, run some tests, and if they are equivalent in the logic, the tool will say, okay, if it's not, something happened, and we must go back and see what happened in the logic synthesis and synthesize the design again. But EOSIS is a very complete tool for this first step of logic synthesis. Well, some strategies will be applied, and we'll see if the designs are equivalent. But also during design, we must to ensure that our chips, after manufacture, are testable. So we need to make some strategies and insert some strategies in the design even before the chip is manufactured. And this is what we call design for testability or design for test. And in the modern area, like 30% of the area that the chip have are only for devices that will be used to test the chip after manufacture. Because during the process of manufacturing a chip, it can, because we are working with very small things, and can be some short circuit inside, or something get a little bit wrong and have electromigration between the metals. So we must be able to check that. And if we don't have some internal mechanisms to make that, it will be very, very difficult, because after manufacture the chip, we only have access to the input and the output pins of our chip. So during design, we must have that in mind. And we have a tool, open source tool called FOT. This is provided by American University of Cairo. It's a very good tool to insert some mechanisms inside of our design that will allow us to test our chip after manufacture. And there are a lot of strategies for example, using scan paths inside our design. And it will allow us to make the chip more observable and more controllable after manufacture. We can also make some, design some vectors inputs to express our design after the manufacture, and FOT also provides those functionalities for us. So another open source tools that we can use to perform some tasks that all the companies are doing in their designs along the world, along the industry. So we are also covered for an open source tool to do this kind of stuff in our designs. Well, I guarantee that my design will be testable after manufacture, but I need to ensure that all the transistors of my design are respecting the time constraints that I have, because I don't want to to insert some data in the inputs and wait for a long time, or cannot be able to perform it because it's not respecting the time constraints that I have. So here we can use in OpenSTA, it's another tool. This tool is generally embedded on OpenRoad, but we can use that in a separate way. And OpenSTA will check if the design is respecting all the time paths that we have. And when I talk about all the time path, it will check if when I put input, the input is stable for a long time enough to when I have a clock transition, it will be stable to be latched into our flip-flops, but it also tests paths that don't go for any flip-flop or register devices. It will divide all my paths that I created in the synthesis, and will check for everything, so I can ensure, okay, it's good, it's respecting my time constraints, so after my design is manufactured, it's everything okay. I'll do the same verification of timing analysis later, because I did synthesis, but also later I'll be making the physical synthesis, so I will change some things internally, so I need to perform STA again. Here it's a first step. Okay, I'm respecting until now, everything is okay, you can move along for the next step. But if we see here some violations, I also need to go back and maybe insert some buffers, or to strain the signal, or to make it slower. Because in the perfect world, I want to put an input here, and the output is immediately observable. At the same time, I want to insert the clock. Well, I want to insert the clock signal here, and I want it to reach every flip-flop at the same time. It's not possible. So the tool will perform some tasks that we have the same time for everything, make the illusion that it's immediate, but it will not be. Now we start the fun part, the part I like the most in the digital design, which is the physical design. I validate the logic of my design, I map to the technology that I'm going to use, but now I start to design how the things will be physically inside my chip. So I have my gate level netlist that I will provide for the tool, and here we are using OpenRoad. This is also the state of the art for the physical design of a microchip. It's open source, you can use it, you can integrate in the tool that if you want to design your own tool. It's very accessible. It was started to develop in 2018. It supports most of the open source PDKs and also some PDKs that are proprietary. Of course, to get access to that, you will have to go a painful process of getting NDAs and so on so far, but we can use the open source PDKs as I already showed. And here in physical design, we divide in some sub-stages, and I'll go one by one, explain what it does. But basically here, for the tool, we send our gate level netlist that EOSIS provides us, and here we must send to the tool a lot of other files that are provided inside the PDK. Because now we are building things physically, so we must send to the tool the rules for laying the metal layers, and also the logic gates, but now not only the logical view. Now we have to send the tool the physical views that the foundry designed for us. The first step, we will define the foreground, and we will specify the die area and the core area and the areas where I say the tool. Okay, this is the definition of the foreground. You must place the standard cells here. That's my constraint, and the tool will respect that, because we cannot just place the logic gates anywhere we want. We must respect some rules to allow that the standard cells will have power connections and will work fine and will be manufactured. So the first step is to create this floor plan. We also create a power plan, and we create a mesh where we are going to use to distribute power along all the logic gates. And then we go to place the standard cells. So here I place an image for the GUI of OpenRoad, and all these little rectangles are standard cells, different ones that my EOSIS tools mapped to create the logic I'm designing. We also put some tap cells. Tap cells are special cells to polarize our technology. Some technologies need that, some don't need. So in this case here, the technology needed. Well, tap cell is just a simple cell to prevent latch up and to polarize the substrate of our standard cells for this technology that I was using. After we place, we want to create a clock tree, which will allow us to distribute clock for all the sequential devices that we have in our design. It's very good to make things stable, and as I already said, I want that my clock arrives for all the sequential devices at the same time, but it's not possible. So we make a tree, and the tool will perform a lot of complex algorithms to make the signal to arrive all the sequentials. It is distributed in a hierarchical format, and all the different colors here are representing different levels in this hierarchy. And after that, I start to making the physical connections. I have the logical connections from the IOSIS tool, and here is how the tool will perform. We generally stack different metal layers and we make connections that we call vias, those little connections here in the vertical way. And every layer here is a different material. Of course, between those layers we have insulation to prevent shortcuts and many other stuffs, but this is only a representation of what is a routing process is. Here another representation, different colors, different type of materials. They have a preferred horizontal or vertical preference when placing those different metal layers. And as I said, here the logical connections will be established in a physical way. So the tool will design some rectangles saying, okay, this is the amount of metal that during the manufacturing process, the tool and the foundry must place it. It must to have in this space, this width. So the tool will also perform a lot of algorithms to do that. Then we get our final design. Of course, if we take a look, there are some empty spaces in our design. So it's not quite ready yet to send to manufacturing, because during the manufacturing process, we cannot have empty space. It would be very difficult to make masks that, put some metal here, jumps and put in another place. So what we do? We don't need that space for our logic, because all the logic gates we need are already placed, are already routed. So we just put some dummy cells, which we call filler cells. And those cells don't have any logic. They are just to making the metal layers continuous. And now we have our design complete. And we can, here is just a block, and we can integrate it later with our top block. Of course, here we can make some tests again to check if the tool didn't change the logic of our design, and we can perform some simulation again to check if everything is okay. Because if something changed, I can go back to the tool and perform physical synthesis again. But
sorry. Do you have to manually put the cells in your floor? I mean, how does that work? Because
no, anything we do here, it's manually. We can do some adjustment, but everything we say, we pass the files to the tool and say, this is the files I need you to place. This is the constraints you need to place in this location, and the tool will perform it for you automatically.
And the same for routing and all this stuff.
The same thing for routing.
And another thing, of course that this tool might know all the constraints, but if you, eventually, depending on the routing, you may have delays in the signals and that kind of stuff. So do you have to run static analysis again and try to figure this out?
Yeah, I'll go later, because we must to make some steps before. And here, after routing, we must to check if the tool did not place the routing layers in a way that it's not possible to manufacture. So we have some design rules that the founder provides us, and we send to the tool and say, based on these rules, check if my design has some violations. And it will look for violations like the distance between the same metal layers, or different metal layers, or the width, the metals, if they are respecting everything. So after I make the physical design, I run those checks to see everything is working fine. And if it is, I'll make some checks of logic. If the logic didn't change, I'll extract from the physical design some netlist, and I will compare with my coding again to see if everything is okay. So this is a step we call LVS. And now we make some extractions, because now I have metal layers and metal connections, and those metals there have resistance and capacitance. So I will extract those informations, because those informations will impact on my delay of my design. So now to make a more realistic static timing analysis, I'll input those informations, and using OpenRCX, I can extract the capacitance for the metals based on the information that the foundry provide me, the rules that the foundry provide me, and it will calculate based on the length or the width of the metal layers, and I can make a more accurate static timing analysis. And if it passes okay, I'm able to integrate in the top design, because this is only a block, but if it was my whole design, I would place the pads and send to the foundry to manufacture our chip. So this is the basically flow that we usually do. As I said, it's not linear. Most of the time we must go back in some stages. But usually this is what we do in the industry. There are a lot of tools to cover all those steps. And just to share, this is a RISC-V core that we are designing in Osiris. It was accepted in a IEEE CAS program, and probably we are going to tape out. We are going to send to manufacture in the end of the year. So this is a very good milestone for Osiris. It's a simple core, but it will be very great to have our own chip using the flow that I presented here, only open source tools, only open PDKs. This is a flow that we designed in Osiris that we call OsiFlow, but it is not the only one. If you look on the internet, we have Hammer, OpenLane, Silicon Compiler, and many other flows. You can choose whatever you want. Most of them works with all the open PDKs. I hope that I instigate you guys to take a look on hardware design and open source tools. There are a lot of space to work on design hardware, but also on implementing features and improving the open source tools that I presented here. So thank you very much, and I'm open to questions. Go ahead.
Excuse me. Is that package that you mentioned on the first part about your development, does that package have any kind of profile that could you report us some error or even critical paths along your design? Because I see that you have many steps even before your physical design. So is that some insight that you could have along your development to improve even before you take this path of even on design for test?
Yeah, of course. The tools generally reports you things, and you can see, okay, I have a area report during your design or during your synthesis. So the tool will always give you some reports, and based on that, you can analyze it as a digital design and see, okay, it's good, or I can improve more, and you can make the constraints more strictly. So you can run again the step and see, okay, I improved this, or no, this is not impossible because it will violate some of the things I'm trying to do. So all the time you can have feedback from the tool to check if your design is okay and if it's able to make more improvement on that. So every tool has this capability.
This includes YOSs?
Yes, YOSs too. Okay, go ahead.
Could you comment a little bit about what kind of features are currently missing in the open source tools like OpenRoad, which would be quite interesting to advance the tools? What, not just on OpenRoad, or maybe what are the key things which are missing on these projects?
What I can tell you is about FOAT, that is designed for testability. That tool is under development. It does some kind of things, but not cover all the things necessary to make DFT. So we can use that to improve our design and to make sure that we are going to be able to test it after manufacture. But there are a lot of things inside FOAT that can be improved. About the other ones, I most of the time use the tool and not all the functionalities inside it. So I cannot tell you what we need. But for simple designs or designs that are used in the IoT industry, for example, the basic examples, the tools are very, very solid on that. So I cannot give you an example because everything I use, it performed okay. And there are a few comparisons with some features that are very better than, proprietary tools.
But in your case, in the case of your research, for instance, it's just a matter of using that to produce, new SOCs or also to improve open road, like to implement something which is already published in a paper, for instance, or there is some also research you do like to develop new let's say unforeseen features, which are necessary in the field.
Yeah, what I say is, and I have a few friends from the lab I'm working, they are improving some features in the tool for routing and for placement using machine learning and artificial intelligence, which is things that the companies in the industry, the proprietary companies are doing, and they are doing this. And for a PhD, he had a very good results on that. So it's good that they are putting machine learning and artificial intelligence on the tool, and we can compare this with the industry. So there are space to make improvements, and they are getting very good results on that.
I see. So one field which is interesting for the open source tools would be like to optimizing the placement of the cells in the die, for instance.
Yeah, for sure. There are a lot of space to improve the algorithms that they are embedded in the tools. So there are research. I have colleagues that have been working many years and making short improvements. And then you can submit, and they will check. And if it's a very good improvement, they will attach to the tool.
Thanks.
Behind and okay.
Yeah, yes. So after the placement phase and the routing phase, can you use the tools to simulate and check if there are any overheating area that you need to fix?
Yeah, I didn't show it here, but OpenRoad has some features to check, congestion and heat maps, and you can see where are the places that you can maybe spread a little bit or change a little bit the placement area, put some constraints to the tool to spare a little more the standard cells. Yeah, there is features to do that. I just didn't put in the slides. Go ahead.
So, just out of curiosity, so in practice, when you're designing a chip, how much of that entire pipeline is automated, or how much do you actually have to run each tool, or requires some interaction from the developer designer? So, in practice, how does it happen?
The idea behind OpenRoad was building chips fully automated in 24 hours. So the idea was just to play a button and, of course, passing your behavior model of your design, and it will give you the output that was the file that you sent for the font. Of course, in my experience, it's more productive if you have control through the steps, because you can make improvements in your design, you can make checks during the steps, but the idea behind OpenRoad was just to play a button and have the design later. The flow that OpenRoads provide us, I kind of see very complicated because you don't have what's happening. It's a huge bunch of make files, calling scripts, and I feel kind of messy, but this is a flow perfect just to put a button, to play a button and to have your design. But because of that, we were creating OSIFlow in the Osiris group because we have more control in the steps and we can make improvements and see the reports from the tool step by step. Behind that.
So, how widespread is in the industry this open source?
I see a few companies or startups using those flows. In the latest years, we see a lot of movements, and we have companies that are making some movements to make the community use more. For instance, there are some open shuttles that give us the opportunity to send our designs and they will manufacture, because manufacturing a chip is the costly part, I think. Design has its own expenses, but there are a lot of competitions about using open source AI features to design your chip and to make. So I see in the recent years a lot of movements to spread the idea of using those open source tools on any flow you want to design your chip and have the possibility to manufacture it.
If we look at, I don't know, Cheapos or Idea, these big companies, is this just the start or it's really a serious thing happening right now?
I know a few companies in the world that are using open source tools to make their design, but in the industry, they are not using open source tools to do the design. But the things I can learn using open source tools are very similar with proprietary tools. So if I learn something in an open source tool and how the flow works, it's very, very similar. The commands sometimes look familiar. So I think for us, learning open source tool will be a huge step to using proprietary tools that generally are the tools that the companies are using. I don't know if you have any other.
Do you have any knowledge about the state of the international um, chip manufacturing industry here? Is there any foundry here in Brazil which can produce the chips which are designed, which are the result of this workflow?
Not really. We used to have Seitec, but it was a long process of that, and I'm not sure, but I know that Brazil doesn't have any company that manufacture the chip and have, because most of the time when we start a design, we already choose a technology. So if I'm choosing a global foundries technology, my design will send to global foundries to manufacture. I cannot choose a technology and send to another company to manufacture it, because they have the knowledge about the processes, and sometimes most of the time you must sign an agreement that, okay, I'll use your PDK, but I'll just send to you manufacture my chip. But in Brazil, we don't have
Any technology.
I think that's it.
All right. Thank you very much.
Thank you very much.
All right, everyone. Good morning. I'm Mikhail, and today we're going to talk about RISC-V. As the title says, it's an introduction to RISC-V. So we'll see a little bit about its history, a little bit about its instructions, instruction formats, about its extensions. Extensions are a big part of RISC-V, and at the end we're going to talk about profiles. So first of all, who am I? Who is this random guy talking about? We are an open source consultancy. I'm from Manaus. This is a picture of our beautiful city. I have a PhD in computer science, and I mainly worked during my academic years with formal verification, mostly focused in C++. So it's a way to verify a program without testing it and prove that the program is correct. Today I'm working with RISC-V, specifically porting the LLVM libc to RISC-V. I will talk a little bit about that at the end. And he's my contact if anyone is interested. It's just mikhail@igalia.com. Okay, so let's start. What is RISC-V? So RISC-V is open instruction set architecture, as known as ISA. You're gonna hear that when you talk about instructions. It's not a chip like Intel, the Core i7, and it's not a piece of IP. It's like the ARM Cortex-M. It's an ISA just like x86, ARM64, which we usually write as AAR64 or PowerPC. Little bit of its history. It was started in 2010 at Berkeley. RISC stands for Reduced Instruction Set Computer, and it's 5 because it's the 5th iteration of its design. And in the next year, 2011, we had a first specification, basic specification, and we already had a first type out in the same year. And in 2015, the RISC-V International was launched, which is the global foundation behind the RISC-V. And in 2023, this year, the foundation released this market piece that tells us there are around 10 billion cores. These are not processors, right? So cores, so you can have more than one core per processor. So today we have 10 billion cores in the market. I have one here with me, actually 4. So there are 4 cores here. This is a Sci-Fi 2 board. As you can see, it's roughly the same size of Raspberry Pi. Has 8 gigs of RAM, and it's a quite nice board because it was mass produced through Kickstarter. So people were there and they crowdfunded and just mass produced this board. And a really nice history of the board. What makes RISC-V so special? So first of all, it's free. So let's say you want to design an ARM IP. You have to pay a upfront license, which is around $10K to $10 million. You pay 1-2% on the total price of the chip, and there are rumors that they're gonna change this license, that you're gonna have to pay based on the device price. So it's very expensive. They dominate the market, especially on mobile, so they are pushing the limit there. Let's say you wanna design a x86 core like Intel or AMD, forget about it. They are the sole owners of, Intel is the owner of the IP, if I remember correctly, and they have an agreement with AMD to produce it. On the other hand, RISC-V is free, so you're free to use it, to extend and customize it in the way that you want. It's open, so it's designed on a BSD license. The RISC-V Foundation, RISC-V International now, is the owner of the IP, the license, and they are licensed now under the Creative Commons license. After the RISC-V Foundation was created, they moved to Switzerland, like to be more neutral, and they renamed to RISC-V International. And in their the founding documents, they say that it doesn't have any intention of commercial use. They are non-profit. They are only the governing body of the specification, in the sense that they help design discussions and to push forward the ISA. It's a singular universal ISA, so it's designed to support both embedded device and higher-end servers. It's designed to all the microarchitecture styles, so you have in-order and out-of-order execution, you have single-use, superscalar, and is designed to be extended for more specific use, so like AI-specific, graphics, etc. It's a fresh and a new ISA, and I think the most important part is that it's simple, right? It's modular, we're gonna see that later, but it's really nice that we have a simple ISA. In comparison, let's see x86, 64. So we have 3,600 instructions, and if you want to read the manual, it's 5,000 pages long. So imagine the hardware design have to design everything, right? It's really painful to do that. So ARM is supposed to be also a risk reduced set of instructions architecture, and its manual has 2,700 pages. It's massive as well, and we have stuff like this instruction. It's an assembly that loads multiple increment address on equal. So it has 5 loads. It writes to 6 registers, and only if equal is set. So that's equal is set on the control register, and it writes to PC and performs a conditional branch. So imagine this might be very useful in some cases. I don't know where, but if you want to do all of that in a single instruction, you can do. By the way, I'm going to talk about some assembly here. If you're not familiar with assembly, don't worry. I'll try to make it as simple as possible. In comparison, the RISC-V 32i, so RV32i specification, all fits in a single slide. So we have some integer computation. So we have add and subtract. We have Boolean operations, and or short operations for integers. Shifts, we have load immediates. So when you hear immediate, you think constants. So we load constants. We set flags. We have control transfers. So mean branches. So think C or any other language. We have ifs. So that's a branch. We have jumps. So in an assembly code, we jump for another instruction, not right next the next one, but you can jump for arbitrary pieces of the assembly. We have loads and stores, load from memory, store to memory. And we have some miscellaneous instructions, so fences for concurrency, for out-of-order execution, in-order execution, and we have calls and breaks. So these are all the instructions you need support to be compliant with the RV32i. Registers, we have 32 registers. I'm not going to go in detail through all of them. One nice thing was actually mentioned in the previous talk. We have 0. So this is similar to ARM64. We have X0, which is hardwired to 0. So you always have 0 in that register. You cannot write to it. Everything that you write to this register is ignored. We have our usual stack pointer, global pointer, thread pointer, frame pointer. We have 8 temporary registers, which is so nice. If you ever worked with 32-bit architecture like ARM or MIPS, then you only have 4 temporary registers. It's a pain to try to make your code work with just 4 registers. It also has 8 function argument registers when you pass arguments to functions. So, for instance, if you have MIPS 32 only have 4 registers. If you have a function with more than 4 function arguments, you have to push into the stack. And it has 12 safety registers for calling safe functions. So it's a very nice set of registers if you want to develop for RV32. And so here are a few examples of a few instructions, and they are all divided in a few types. So there are 6 types: RB, UI, S and J. The most important thing about these instructions is that they all place the registers in the same position in the instruction. That means that you can, the hardware can read the registers before they can decode the instruction type, right? And you can have instructions that can fit up to 3 registers. And as we're talking about a 32-bit architecture, all the instructions are 32-bit long. Some design choices of RISC-V is a load store architecture, so every operation is register to register. It only has one addressing mode, no trap for arithmetic overflow, no delayed branches and delayed loads. Delayed branches are very interesting concept. So in MIPS, if you have a branch, so let's say you have an if and you jump to another position, in MIPS, 1 or 2 instructions after you jump are executed, right? So it's a strange concept, but it can be useful in a few occasions. The program counter is not a register, it's RISC-V. If you want to read it, the program counter, you can use these instructions, this instruction. So it's add upper immediate to PC count with PC counter. So we are reading, we are storing the result of a constant plus the program counter and store it on a given register. And the good thing is, because the program counter is not a register, we don't have branch instructions. Only the instructions that change the PC can be used with this instruction. So one of the first, at least for me, one of the first confusions I had when I started to work with RISC-V is that we don't have some instructions that are so common on x86. So how do we move the content of a register to another one? In x86 we have MOV, so you just move the content of one register to another. Very high abstraction, but consider moving the content of a variable to another one, assign a variable to another one. So anyone wants to take a guess on how we do this move, how we move the content of a register to another one?
Add 0. Please comment.
What?
Yeah, do you add 0?
Yeah, great. That's actually what we do. That's a great. So you win a T-shirt because you got answer. You.
No, I
I'm
cannot.
not gonna give it to you because the experience. So
That's good.
so you get a T-shirt. Okay, another question. How do we branch with equal to 0? Yeah, but. Yeah, that's the question was not very clear, but we don't have 0, right? We have register to register operations, so yeah, you get a T-shirt too. There you go. Okay, another question: how do you negate a register? So we have a value inside the register, and how do we negate it? No, you already answered. Anyone wants to take a guess? No.
XOR?
We do assume and 0, right? So that's, and then we saw the content again on the same content. That's how we negate it. Okay, last question. How do you jump without saving the return address? This is a bit more complex. Yeah, I think you don't have enough information about that, but you just store the return of the jump to 0. As I said previously, we don't. If you write this to x0, it's ignored. So you just do the offset and jump, and you don't store the return. Okay. But we also have, and like in the assembly, we have some pseudo instructions. Even though the ISA doesn't have these instructions, we can write them, and the assembler will generate the ones that we want. So we don't have MOV, but we have MEV, and the assembler will just generate this for us. We can branch equals 0 and not use 0. We have nag to negate the variable. Yep.
How do you make it floating point operation?
Oh, so the RV32i doesn't have floating points. We're gonna talk about that later. Right. So we have all the flavors of RISC-V, we have RV64i, which introduces 64-bit registers and 64-bit addressing modes. And we have new instructions for words and double words. We have RV128i, which today I don't think we have any hardware for that. I think if you read the RISC-V specification, it says that the top computers in the world today use 50 bits for addressing mode, but they project that by 2030 we're gonna need more than 64 bits to address memory. So the exascale supercomputers, and so that's why they already have it on their specification. And we also have the RV32 and 64E, which stand for embedded, and as the specification says, I'm sorry, it's too small. We have 16 registers instead of 32, and if you have the encoding for the other registers, it's reserved for specific use. Okay, so this is basic RISC-V. We only have integers, we have load stores, all of those instructions that I mentioned, and the good thing about RISC-V is that we can extend it, right? So let's say we want to multiply and divide. We don't have that in the basic specification. And so we have this extension that we call M that adds divide and multiplication extensions. It adds some new instructions. So we have mul, age, div, and rem. So you multiply instruction integers. You get division, you get a quotient and reminder. And the good thing is that the core, the specification can choose to implement that. So that's the beauty of RISC-V. You can choose to extend your core, your design to support these instructions. And if you do, now you don't call it RV32i anymore. It's called RV32i-M. So because of the new extension. Let's say you want to use floating points. So there's an extension for that as well. It adds new floating point. Oops, what happened? We have new floating point registers and floating point instructions, and it's a nav extension. It adds float add, sub, mu. It adds fuse multiply add. It adds square root. And now we have RV32i MF if you support single precision floating point. Well, let's say you want to support doubles, right? And we have an extension for that, which is called D. And now your core is called MFD. Let's say you want to support economics. You have the A extension, MFDA. Let's say you have a control status register like ARM. So you have MFDA ZICSR. And let's say you have fences, right? So now you have MFDA, ZICSR, ZI fence height. And as you imagine, this gets big. And eventually we shorten all of this to G. So if you see this in the wild, RV32G, RV64G, that means that we support all of these extensions. This is usually the basic, the more common way you see in the wild. Okay, so let's see you want to compress instructions. What are compressed instructions? So remember that I told you that all the instructions are 32-bit long, but we want to compress them and to make it cheaper to produce the chip. So every instruction, there is an extension for that, C, that expands compressed instructions to uncompressed ones. And think of it like arm thumb. You can compress the instructions and make it smaller. And the great thing about it is that the compiler doesn't care about it. You just generate the instruction and the assembler looks at your code and compresses it for you. And if you support it, now you have GC. So RV32i GC. And we have more extensions, right? RV is about extensions. So let's say you have no standard extension. So think about it, think of it like vendors specific extensions. You can add an X. You want to do bit manipulation, you have extensions for that. Vectors, extensions for that. Half precision floating points, why not? You already have extensions defined for that. bfloat 16, which is usually used for AI. More extensions. Cryptography, also extensions. And if you want instructions that don't that change behavior, specify behavior, we also get that. And you can imagine where this is going, right?
A few moments later.
You get this. I'm not gonna read it, okay? But this is a very common way of.
What the size of the IC with this?
Yes, big. So this is a common extension, actually, a common ISA, and we're not gonna keep writing all of this, right? And how we deal with the fragmentation, right? This is common, but let's say a vendor doesn't want to implement all of this, just part of it. So we have profiles. So this was it come up from the RV International, and it's a way to provide this portability between all the extensions. So now we have profiles that defined by year. So we have RVA 20U64, 22, and 3. They are defined by the year they were created, the profile, and by the year. And think of it like the microarchitectures on x86. So we have V3, V4, etc. And now that big string of ours just become RVA 23U64. Right, so we don't have to keep writing that all the time. So wrapping up this talk, a recap about RISC-V. It's a free and open ISA, very simple, but with tons of extensions, and because of that we have profiles. And if you want to know more, I'm gonna give you some suggestions. So this is a very nice extension for RISC-V privilege ISAs. So think of it as instructions that can be used by your hypervisor, but cannot be used in user space, can be used by your OS, your kernel, but not in user space. It's a very nice extension, and it's very detailed, and it's very nice to read and learn a little bit more about RISC-V. If you want to buy a book, this is RISC-V Reader, and a very nice book about RISC-V. I didn't read it at all, but it has a lot of information. It's really nice. If you want to try a simulator, there's a tool called Spike that you can use to run your user space programs. You can also use QEMU to work. Actually, I use it daily when I'm developing QEMU. You can also try to build your own core on Chisel. So Chisel, it's a scalar tool, and you can design your own core there. It's very simple. So as you can see, RV32 has not a lot of instructions, so it should be very simple to implement that. If you want to work on a bug, right now RV32G is limited in the Linux kernel to address only 1 gig of RAM. So I have friends at Igalia that have been constantly nagged to fix this for me, but they are ignoring me. So if you want to try to understand more about the architecture and learn more about the kernel, I think this is the great way to start. And finally, what are we doing in Igalia related to RISC-V? So I have 2 colleagues working on different things. So Bolt is a tool that started in Facebook before it was Meta, and is It's an optimizer for binaries. It's similar to profile guided optimization, but it works on the binary, so it's a very nice tool, and it's been ported to Bolt. And if you want to read more about it, I don't expect you to remember this, but just write porting Bolt to RISC-V on Google. You're gonna find this blog post. It's very detailed. It's very nice. We have Luke. So that was by Job. We have Luke working on supporting vectors on LLVM. These are PRs on the LLVM way of identifying them. So he's been working for, I think, 1 year already to support vectors. And I am, as I said earlier, I'm working on libc, the LLVM libc, which is a very nice piece of software that is written in C++. So we have a libc that is written in C++, and RV64G was completed last May, and I'm working on 32G right now. One of the requirements to have it fully supported in the LLVM is to have build bots, and we have build bots that should be up soon. They are using QEMU because we don't have hardware, RV32G hardware, so we are emulating all the system. And that's it. Thank you very much for listening. Any questions? Yep.
I mean, one of the issues of having those extensions guaranteeing that software developed generically run on all boards or implementations. And how is RISC-V guaranteeing this is happening with so many different...
Yeah, so the thing is, the RISC-V doesn't guarantee it.
Yeah, I'm saying RISC-V.
So the vendor has to give you the profile. But yeah, that's a good question. There's a thing called feature detection on the hardware, so you can check in runtime what's supported, and you can have your code with instructions that are supported, and you just jump for them when you need it. Let's say you have a piece of code that does vector operations and another piece of code that doesn't do them, and when you start the program, you read the features of the processor, and then you jump to the piece of code that is supported. Yes, it will increase the size of the binary, but yeah.
What about more fundamental features like floating points?
Yeah, so as I saw in the wild, everyone supports the G extension. So you're guaranteed to at least have floating points, doubles, integers, and whatnot. Atomics, fences. Profiles are a very new thing, and I think it's the first time I saw a profile in the wild. It's LuaJIT. I don't know if you heard of LuaJIT. It's used on NeoVim, for instance, and they define that your hardware needs to be compliant with the RVA 22. So you also have software that defines the minimum requirements, otherwise they will not run.
Just to answer the question from Basket, there is a Basket group called Unified Scumber. They are writing how the extension or instructions is going to be defined when you start using a given chip. So there, it's a mess, but they're going to define that. And that Basket group started 3 years ago, and died, and they are returning right now with a new chair and vice chair. So they're going to define that by the end of the year.
Yeah, so for instance, I was working, before I started to work on libc, I was working with WebKit, and we do JIT there. And so we just basically support RV32G. Even if your hardware does, I don't know, vector cryptography stuff, we just don't generate instruction for it.
Yeah, but then you lose performance.
Yeah, at least you don't crash, right?
Yeah.
Yep.
Yeah, so my question is if you have an idea, you can give us an idea of which boards are out there, what are industry using?
Yeah, so you can get one of the Sci5 too. I think it's around $100. I bought mine like 6 months ago. It's a Chinese website, Yonggi Jung, Yonggi Jing. Yeah.
Allnet, a website called Allnet in China. They sell all kind of
Okay. Yeah, this one I bought is like $100, and it's not as cheap as a Raspberry Pi, but you can find them.
We have more, like, we have these Star 5 producing those kind of boards. We have Sci-Fi doing more boards.
Oh, yeah.
Sci-Fi is going to
This is stuff. Mine is sci-fi. Mine is sci-fi.
Sci-Fi, they sold out all their boards when they launched. We have Intel working with Sci-Fi to produce a more capable board. That's under discussion about when they're going to launch it. That's going to be called Force Creek. We have a startup from China called New 5. They have, say, the best desktop right now. It's a Use 5 beta desktop that allows you up to 128 gigabytes of memory. Has a 10 gigabytes.
I think they are producing a tablet now, right?
Yeah, we have tablets.
Yeah.
We have a laptop. Laptops are expensive right now.
Yeah.
It's using a Use 5 core made by Alibaba or the T-Head, the lab with Alibaba that produces it. It's cost $5K right now, so we don't have a lot. Yeah. And the majority of the companies we have with 5 and 6 are producing IPs. So others can you can buy chips from Alibaba today and from others, but not that much yet. Now you can buy device like Esperanto AI from it's a Europe-based company. They created a kind of PCI card with 1,000 5 cores that you can buy, put in any kind of board, and start doing AI inference. All the NVIDIA GPUs contain RISC-V cores, so you can play with that if you will. A lot of your wireless devices that you use to existing users are using RISC-V. So usually, the easiest way to get started is buying this kind of board.
We also have a friend developing a RISC-V Arc32.
The easiest way is using those kind of boards, or that are you can build kernel on that. I do build kernel on those kind of boards, so you can do anything you want. You can even for that specific board, you can install Debian, Ubuntu, the latest Ubuntu 23.4, and Fedora, I believe.
Yeah.
So it's all running.
Arc as well.
Yeah, so you can a lot of there.
Yeah, the one I have at home, I do all my testing and in the hardware, not the 32-bit because I don't have it, but the 64 one, I just build LLVM, Ubuntu image in the board and just run. It's not very fast, but it's the actual thing running, so you get better results.
Servers coming soon. We now have those kind of companies that integrate hardware looking for RISC-V. So at some point, by the end of this year, begin the next one, more powerful servers will be available. The bottleneck today is the availability of chips. So we have company producing, but there's no guarantee that they can provide a huge amount of chips yet for those companies. Things are flowing. Brazil is producing one. Brazil, there's a group of 5 universities in Brazil working on define a new chip, RISC-V. Things work is going on. So at some point, we can have something.
So Rafael is from the RISC-V International.
Yes, sir.
Yeah. And if you're a student looking for an internship, just ask him.
We have a lot of programs. We have programs with respect to data that we pay students for 3 months. So we pay $6K for 3 months. So we basically work with me on a lot of different projects that we're not moving that project.
All right. Any other questions?
Speaking of internships, is there any reference online about the memory limitation, Linux memory limitation?
No, really.
Just
I actually sent a bunch of emails to several Middle East. Everyone ignored me.
but
I don't think anyone is working on it right now.
But no, I mean, yeah, I guess I'm asking for those references, like the threads that the students could.
Oh yeah.
I believe students are
Right,
quite
so
eager to solve that issue. So
the first step it would be to build a 32-bit image. You can use Yokoto for that, and as a base resource, and Yokoto is a tool to generate images for embedded software. It generates Linux images with all the usual Linux environment, and you can load it in QEMU, includes the kernel and everything. I don't think there is any discussion right now public about it. I've sent a few emails, but I think I only got reply from the Yokodo team because I thought it was a problem on their side of building the image, but it's a kernel limitation right now. Yeah.
So what is the status like upstream for RISC-V and those boards?
And what?
Like Linux kernel.
So Linux kernel, I think 6.1 or 6.1 loads and runs just fine. So that's the latest LTS on Ubuntu. It doesn't read all the sensors. So my board has sensors for temperature and stuff that you cannot read with 6.1. But I think on 6.4 or like Sci-Fi, at least for my board, you can get everything you need there.
Yeah, continue the subject.
Yep.
How about the peripherals, like GPUs, I don't know, cameras and other things? Are they the ones that are already used by other boards, or do we need a special driver? Are they support? Are they
No, not really. If you have a Linux kernel, it should just plug and play. It should work. My board has a HDMI, but the HDMI doesn't work yet. So you have no video output. You have terminal, but you don't have video output. There is a closed source drive for that, but I don't think there is an open source drive for it. Alright. So I think right now HDMI is the only thing not working properly.
But like from what I talked to you yesterday, if it's an imagination GPU, they are starting to upstream the imagination driver.
Okay, yeah, I don't know, to be honest.
One thing that interesting is that 2 or 3 months ago, we launched within Linux Foundation a new project called RISE, RISC-V software ecosystem. It is hosted under Linux Foundation Europe, which means that that specific new project is going to focus on the software for RISC-V. So we have companies like Red Hat, which is a member, a premier member, Intel, and others doing just software. We, with RISC-V International, are going to keep maintaining the ISA and do all the hardware stuff, and the RISE project is going to focus on software ecosystem, which means that Oracle or the databases or other companies that really need to get their software running on RISC-V or optimize for RISC-V can join RISE and work by either paying some money or allocate engineers to work to do the job. So that's growing fast. We have a lot of things going on RISE. We started 2 months ago, and a lot of they even completed the support for Kubernetes in 1 month. So things are moving way faster than we thought. So RISE is a good way to stay in touch or get the up-to-date information about software ecosystems on this cloud.
Yep. 2 questions. First of all, I would like to know more about bottlenecks on embedded systems.
About what?
On embedded system devices. Is there any profiling about energy efficiency or even some comparisons with the actual processors on embedded devices?
Not that I'm aware of. So profiles are mostly related to extensions, so it's not a specific, I don't have a profile for power, for instance. They are defined about the general set of extensions.
That depends about these extensions.
What's defined by the committee in that year.
And just another question. I'd like to know if there are any open projects that we can contribute by or even learning by.
So the LLVM libc, it's a very nice project if you want to learn about RISC-V. There is very little assembly there. It's written in C++, but you can learn about the structure and how we do, for instance, startup. How do you do CRT0 on a program? So you can just look at the code there and check how we do for RISC-V, how we set the registers, the global pointers, thread pointers, and everything. I think it's a great project if you want to learn a little bit on how the things are done in runtime and how things are working. For more low-level stuff, I would just say go look at the kernel and how the specific parts of the kernel are implemented for RISC-V. Yep.
Does RISC-V International provides any standardization on the boot process, or is like
On the what? Boot process.
Yeah.
Yeah.
There's a test group called BRS we started 1 month ago. They're going to find everything regarding the boot. So I mean that's mailing list is already there's a mailing list that Google above the mailing list on Google Boot. We decided to make that an external one, and right now people are sharing a lot of ideas about how to make that happen, including implementation. So it's happening right now. If you want to see what's going on, just try to make it easy.
Okay, any other questions? All right, we're done. Thank you, everyone.
We will be back in 15 minutes, more or less, for the next talk. Okay? Thank you.
Hello, good morning. My name is Eduardo, and today I'll talk about the IoT architecture in the tiny machine learning age. So, I'm a little bit nervous, so sorry for something, but I'll try my best today. Actually, I'm working at Senai. Senai is known by our vocational training, but also we have Institute of Technology and Institute of Innovation. And I'm working at a new Institute of Technology in São José dos Campos. It's relatively nearby here. And we are starting a new area in Industry 4.0 and Technology of Information and Civil Construction. This is the three main areas of that we're working in São José dos Campos. And today we started to talk about the IoT architecture. So generally, when you talk about IoT, the architecture of IoT is typically constructing layers. So we have a close layer to the physical layers. So we have here the sensing layers, like a sensor, actuators. So in general, we have a data gathering. So we start a hardware very close to the physical world or physical computing process in the IoT architecture. The next level, we have the network layer. So we have to communicate my sensor, my actuator from the internet. So this is the basic idea of the Internet of Things. So we started to connect things on the internet. But we do disconnect for something. In general, the common application, for example, if we want to turn on or turn off a light, we don't need, for example, a processing layer. Just a 3 layers is sufficient. For example, we designed an application, put a button in a mobile application to turn on and to light a light, for example, in the case of home automation. But for industrial, it's necessary to get the set of data from different equipment and make some processing data in this case. So this is a typical 4 layer. In general, for home application, we use 3 layers of IoT. In some cases, we have 5 layers. For example, we have a big industry that needs get information about the supply chain and more business information. So we can put more layers in this case to complete the scenario of IoT. But in general, this is the construction of the IoT architecture. We starting from sensing layer or actuator layer and go up depending on the application that we are working. But now, recently, we have started a new era or a new age with the machine learning using this tiny device. When you talk about tiny device, the key point is that tiny device, we are talking about the low power consumption, easy to deploy using batteries. For example, in agriculture, we have some cases that some device can collect data and using a battery for 5 years, a unique charge for 5 years. So it's a very tiny consumption of energy in this case. So when we talk about the tiny devices, we talk about this very low consumption and also the cost of production of this kind of device is also very low. And in the past, a common approach is we have cloud computing. Everything thought that it's possible to send our data for the cloud and process and make some machine learning at the cloud. But in reality, we have a lot of problem with connection of the data and sending the data from the internet. For example, in agriculture, it's very difficult to send massive data for internet processing. So we evolve to mobile. In the mobile computing, we have a very powerful equipment, but the cost of this equipment are relatively high for application in industry or in a lot of applications. And also, the consumption of energy of mobile devices is very high. So we need to plug our mobile phone every day to recharge in this case. So it's not a tiny device. Here is a family of some hardwares, common hardware, commercial hardwares, that we can process tiny machine learning. But what is tiny machine learning? So tiny machine learning is a machine learning algorithm optimized to run in this kind of device. Tiny machine learning is more than deep learning or neural network. Nowadays, it's possible to run neural network in this kind of device. For example, we have a TensorFlow Lite and another kinds of algorithms that's possible to run in this device. We have different applications. For example, we have here some tiny device with camera integration, so we can run some face recognize and image analyzing. This kind of device has a price increase, but for example, Raspberry Pi Pico is the price is low, and we can run a very robust algorithm, machine learning algorithm in this case. So now we can introduce a new layer in our IoT architecture. So very close to the sensing layer. So we have a smart sensors, a real smart sensor that run machine learning inside. In our case, on Sanai, we developed a new tiny machine learning algorithm. So we have a statistical-based machine learning algorithm that uses extreme value theory. This extreme value theory is a statistical theory that works only in the extremes of the distribution. For example, we have a Bell distribution or normal distribution. Instead to see all the distribution of the data, we start to see only the tails of the distribution and create a new distribution function only for these extremes. So if in our case, we are interested to analyze anomalies. So when you work in industry, for example, some equipment can have some problem, and you need to avoid or identify more early as possible some problem in devices. So anomaly detection is very important in this case. In our algorithm, we have this structure, so it's just basically a binary classification. So we verify if the data is in normal state or abnormal state. And combining this kind of processor, now we have this foggy computing. That is, we have a lot of smart sensors with relatively powerful machine learning processing. So we can combine a lot of these sensors and to generate this foggy computation. The data can send, for example, a Raspberry Pi or edge computing system, and now we have this complete scenario for the computation. Not just the cloud. We have the cloud, edge, and the fog computing with a robust processing in this case. Here's some experiment of our algorithm to analyze, to detect anomalies. So basically we have here a Raspberry Pi, Pico W. So we have a gyroscope and Arduino to change the speed of the motor here. So we set two states, the low velocity as a normal state. Algorithm started to learning this normal state, so the algorithm is running on the Raspberry Pi Pico, starting to learn what is the normal, the common state. After some time, or collect some data and try in the classification mode, and we can identify, for example, these points or as anomalies or the change in the speed of the motor. So this is a very starting process, but we can combine, for example, if the system identifies that you have a change we can put different levels for this kind of analysis. Instead of just analyze anomaly, we can identify different levels or different states of the system, combine and make a combination of the algorithm. But you can see here that here we have the variation of the gyroscope, and in this point is the moment that the algorithm can classify the data as a possible anomaly. So we also we can verify if the anomalies occur in sequence, and identify this anomaly as a collective anomaly or an individual anomaly. But the key point is that we are streaming the data from the sensor to the Raspberry Pi Pico, and our process of learning occur in real time. The learning and the collecting the data occur on device, on this tiny device, and in real time process. So this is a big challenge. It's a new, we can identify this as a new age, that we have a tiny device with capability to learn in real time. In general, you have collected data, put the data in a server, train our model, and put the model on device. But now, no, we can learn on real time. This is a big difference for in this case. We test also in a more realistic scenario. So we put here ESP32 board to run the algorithm. We use inverse of frequency. So the motor has a typical frequency operation. So with simulation anomalies, change this frequency operation. So we can observe that we could learn in real time what is the normal function of the motor, and we identify very well this changing in the behavior of the motor induced by the changing the value of the inverse of frequency. Here we have a Raspberry Pi as a broker server, MQTT server. So the data from our board is sent to a Raspberry Pi Pico, and we collect this data on our notebook to complete the scenario of the fog, edge, and cloud computing system. So we can observe that it's possible, it's feasible to create this kind of scenario for real time. The next challenge is to combine for a lot of different equipments and verify if the solution is scalable. So we can a scalable solution for in this case. But the very interesting result is that we can observe very well this changing and classify very well this changing in the behavior of the motor in the industrial scenario. So I think I speak very fast, but this is the general idea of the process, in this case of using the tiny machine learning to construct a new age of the IoT architecture. Some questions?
Any questions to Eduardo?
Yeah.
One question is, you mentioned that it can learn on real time, so I wonder how this works, because usually we have a validated data and then feedback to the neural network. And
in this case, when you have, for example, in the traditional we have a validation data and verify. Now we do not have this kind of the problem here, because we are using a statistical method. We test, we simulate if the algorithm can verify, can classify very well in some situation. We simulate it in another, for example, in a computer, create a simulation to test it if the algorithm can identify very well. But in real time, we have not in this kind of situation. So we need the operator to validate if the equipment, if the anomaly was correctly detected or not. But it's different scenario. But we do not, here in real time, we do not use the validation process.
Is there a name for the model you are using, like BioNet, or something like that?
Just in this case, for example, we are using a statistical-based analysis, like Camins or not statistical machine learning based. In this case, we're using an extreme value theory to create this, but we don't have a name yet.
Anything else?
Historically, computing on these devices have been really hard because they lack capacity. Does your system provide any mechanism to guarantee that operations happen at real time without overloading the processor?
In our case, we started to implementing the implementation of the algorithm. We use MicroPython, and this is the next step. Because for example, we need to put a watchdog or something to verify that the delay in the process this is real time, but this is the next step.
Thanks.
Yeah, but I mean, if you go to there's a TinyML Foundation, right? They have, I mean, there is a huge number of companies working on similar stuff, right? Of course, it depends on your field, on your focus, but this is really a big area that is being developed, and there are some real applications being sold already. Very interesting applications using machine learning in very tiny devices. It's quite interesting. I mean, yeah. If you want to know more, I mean, TinyML Foundation is a place to look for use cases, examples, that kind of stuff. Or read his paper as well, right?
Okay.
Okay, anything else?
So when you use a different model, what do you need to do in this case for this model, so to speak? You need to calibrate something?
Yes, depending on the model that you are using. For example, if you work with neural networking, you need to create the layers of the neural network, collect the data, and train your data. If you are using some statistical methods, we have hyperparameters. So in this case, we verify what the best hyperparameter to identify this kind of anomalies. So we need to create a synthetic data set and select the best hyperparameter based on this synthetic data. But the learning of we suppose that the data has a hiding pattern. And then the method, the statistical method, serves for hiding pattern in the data, on the data. But we needed to calibrate this some hyperparameter. Like for example, in neural network, we have the number of neurons, the number of the layers. Here we have, for example, because we are talking about streaming data, we save the data inside the data window. So the size of the data window is a hyperparameter. So we need to set this hyperparameter. Another point, for example, we are talking about extremes. What is the extremes in the data? We need to calibrate this. For example, the standard deviation, for example, if you have a data with a greater 2 times, 3 times the standard deviation of the mean value of the data inside the window, we can classify this data as extreme. So we use a threshold to select extremes and use these extremes to obtain, for example, our CDF or CDF of extremes of the data collected in the normal state of the data. So it's depending in this case.
I see, and that method is not the same method as neural network or evolution of neural network.
Yes.
It's a statistical one.
It's a statistical one. So we just put here, for example, select extremes and determine the CDF of the extreme value of the Weibull distribution function.
CDF stands for what? Sorry, the CDF is.
CDF cumulative distribution function. So we obtain the statistical distribution function for the data.
Wow.
If we go back to the slides with the anomaly, the graph, yes. So if I understood correctly, you start guessing the parameters. So for instance, I could guess that the average is below 10, and then the algorithm will adjust itself.
Yes. From along the time.
Yeah.
Yes.
Okay.
Yes, we have a window. We analyze the statistical means and standard deviation from the data inside the window, select the streams. But the key point is that we suppose that our system is a normal state. We are starting connected through our device on the motor, for example, and we start in a normal state. So this is a supposition necessary. But if we are in the normal state, the statistical information here is for the normal state. So after some time, we change the speed to an abnormal situation, and we collect this abnormal situation. Yes, it's a dynamic learning, collecting data process.
Well, there's a famous TinyML benchmark called TinyML Perf. I'm not sure. Have you ever looked at this benchmark?
Not yet.
Because there is an anomaly model there.
Yes.
Which is a convolutional neural network there. Maybe it could also be interesting.
Yeah,
So.
it's a good point. I not do it.
How much time do you need to learn the normal pattern?
Depends, because for example, he was very short time, but in the case of the motor, for example, this value indicates the time necessary to learn. So depending, because we need it's dynamic. The process is dynamic. So if you do not have extremes in giving our condition, the process continues learning until to obtain the sufficient data for example, to fill this table, this anomaly, the extreme table. So it's not a linear process. So we have, I don't know how much time. So depends of the system.
Could be minutes or hours.
Minutes or hours, depends of the system.
Okay, thank you very much. We will be back at 2.
Hi, my name is Luke. I'm a student here. This was supposed to be a group presentation, but my partner had some problems, so I'm here alone, but it's okay. So, what I'm presenting today is Malloc Adventures. I'm sure we all had to do with memory allocations and seg faults and all that kind of stuff, but like the more I study here, the more I think that I need to learn what's actually happened, like under the surface. So this was kind of an adventure of me and my friend trying to figure out how do we actually get more memory from the computer. Okay, so malloc and free are the most common way to acquire memory from the heap, right? And we went on a journey to figure out what was there before, like who created malloc and what can we use that's lower level, and how does it work, and mostly why they were created, right? Why do we need malloc? So in Linux we have two main ways to acquire memory from our operating system, in this case the kernel. So we have sburk or burk and mmap, right? So the sburk or burk gets a contiguous amount of memory. Usually it's the largest in your computer, and then it works kind of like the stack. It pushes the pointer forward as you ask it to. So if you call sburk with the number 10, it will give you 10 bytes, right? So, and this image kind of illustrates how sburk might work, but it's not how modern program works. And when we were taught that in class, I always got really confused by this image because there's a stack going down and a heap going up. But that doesn't really make sense because you can have as much memory as you want in the heap and the stack is really limited. So how could that work? So why is Burk not the best? So it has a limited size, not really like the size of the stack, but it's the largest contiguous memory in your computer. And it doesn't work with multiple threads. So if you have many threads trying to access, it's just one spot in memory that they all have to compete for. And so you basically have to do it sequentially. There's no way around it. And it's not really used anymore. Nowadays, we mostly use mmap, that I'll talk about in a second. But we found that it's good for learning how, like in a preliminary way, how we can get some memory, extra memory for our programs. So this is actually how the program memory is stays in your computer. This makes much more sense for me. So mmap is just, it asks for the kernel to give you like some pages of memory that you can use for your program, like mapped memory. So that image that we had before, this is the new version, and it's much better in my opinion because it has like this other piece that there's a pointer to, and which you can access. The kernel can give you access, right? So what? Malloc, the GNU C library malloc, the one I'm pretty sure we all use, is derived from the pthreads malloc that's called pt malloc, which comes from dl malloc. So what's dl malloc, right? Excuse me. DL malloc is actually the Douglas Lee memory allocator. So some guy came up with the basis of our malloc, right? Eventually they dropped the name. But this guy was one of the primary authors of libg++ from 1986 to 1991. So this guy was a pretty good guy and really good programmer. So why? Why did this guy, Douglas Lee, decided to create malloc, right? So it all started when he was creating programs that needed a lot of dynamically allocated memory, and he was like, okay, this is slow. I'm not getting enough performance out of this, so I need something else that will make my programs go fast. So what did he do? He made special purpose allocators for each of his classes. So imagine, in C++, I'm not sure if everyone here is familiar, you can actually override operators, and you can write your own implementation of them. So he started overriding new operators for different classes, creating different types of different ways to get dynamic memory, right? And eventually he saw that that's not viable. He's like writing the C++ standard library, and he was having to do like things specifically for each class. So eventually he realized that that was not really general purpose. He needed something else. So he tried to create a new allocator that didn't tempt programmers to make their own allocators. That was good enough that everyone could use in a general way and didn't have to worry about memory allocation. And also that was fast, because that was the initial problem. And so we tried to create a new malloc, but we did it only tempted by the will to learn. It's not really bad. We didn't try to be better. We just wanted to learn how to create a wheel, so we can then later better understand how the actual wheel that we use is constructed. So we try to implement our own version of malloc. In our case, we only used Sburk because it's much simpler than mmap, but we actually get some promising results. So we tried to implement our own malloc in free, and we tried. Our idea was to have some sort of goal that we knew this was going to be like a toy allocator. It's not really one that you can use in your programs, because it's really hard to top malloc, and you'll see later why. But we tried to optimize it for big memory allocations. So why big buffers? So I actually study computer graphics, and so often I have like huge buffers of vertices that I need to send to the GPU like constantly, and I don't really need to keep allocating and deallocating them. I can just allocate them once, and then they'll stay with me for the remainder of my program. Also, like statistical models, basically AI really uses a lot of big buffers that you need, like the matrices to be allocated, and you don't free and allocate them a lot. So that's our goal with this project. So the starting point. We started from the basics of the basics. We just had stdio for some debugging, unistd for Sburk, that's the function we used for allocating memory, assert for error handling, and pthread just to place a mutex lock around everything, so we don't have many threads trying to use Sburk at the same time. So how did we implement that? The basic idea of our malloc is using a doubly linked list with all the blocks. So the idea is, I'll try to draw it here. I'm a bit old-fashioned. I like to draw things because I know I can like change them better, and it helps with my explanation. So imagine we have a huge block of memory here. And this is the memory we have available for Spark, right? So we'll have, before each block of memory, we have a little bit of metadata. And this data is useful for us to go through them and really see which ones of them are allocated, which ones of them are not, right? So we have a next and path pointer, a status that's basically available or unavailable. The too small there is deprecated, and size. We later saw that this metadata in malloc is much smaller, as you'll see, but we knew that, but we thought that since we were trying to optimize for bigger buffers, like a few more bytes wouldn't make a difference. So this is our malloc function. The basic idea is if we don't have any memory, we need to request more memory. And if we do have like some kind of chunks already allocated, then we need to find another chunk. And you can see like the basic use of the mutex lock. We just say, okay, I'm doing malloc now. I'm the only one that can do this. So you lock and then you unlock at the end. And here is like some pointer mask just to, you have a pointer to here, to the beginning of the metadata, and then you want to actually give the user the pointer here at the end of the metadata. You can actually, like in malloc, with the C library, you can, using some dark pointer magic, you can go back and see this metadata by yourself if you want. And I'll show you how it is so you can actually know what's happening. So, how do we find new chunks? We basically go through the list. Let me draw a few more chunks here. So, let's suppose these two are allocated and this one is available. So, here we'll have a doubly linked list, right? So, this is a two-way arrow, and here is a two-way arrow. So, we basically go through the list asking if, okay, are you free? And then, do you have enough capacity to hold the amount of memory I want, right? And there are many what you call fitting strategies. Fitting strategies are when you, when do you really use the memory? Because imagine this, I'm trying to allocate 10 bytes. And then I find an empty space with 100. Maybe some other guy will come after me and will need these 100 blocks that maybe there aren't any further down the line. So it would be slower. So if you actually go through them and find the best place for you, it's called the best fit. What we used is a first fit, which just gets the first one, right? And we did that because we thought we needed to be fast, and we thought that since we were using mostly like big buffers, they would be usually big enough to fill decently any holes we needed. So the basic idea is we get to an empty space, and let's suppose this is enough. So okay, then I'll check my size. Is this size enough for me? Is this big enough for me? Okay, let's suppose it is. So what do we do next is we ask, how much bigger are you? If you're just a small amount bigger, we'll give you the memory, the extra memory, just because we don't want to have the trouble of having another element in the linked list that's like really small and doesn't help us at all. So we thought that we just give it to the memory so it will have a little bit of unused memory, but in our case it's okay. If it's like really much bigger than what we want, we just split the chunk. So we have another chunk here, this one's used, and then we just insert it in the linked list, right? That's the basic idea. So now for freeing. Freeing with the doubly linked list is really easy because all you have to do is first you check forwards. So okay, is the next element empty? If it is, we have to perform a merge. So we basically, this guy has a size attribute. So we increase the size attribute of this guy to be this whole size. And then this is properly freed. And then we do the same with like the previous chunks. So if this is free, then we have to, let's suppose this is free. Then we check, okay, if my previous one is free, then what I need to do is I'll add to this guy the size of my current chunk of memory. And then we delete them from the linked list, right? So you can notice that the order is kind of important. So you first need to merge forwards and then merge backwards. That makes it a lot easier. So you only have one pointer to one chunk, and then you use this chunk to merge forward, and then the same chunk to move backwards. If we change the order, we might need to use this chunk to move forwards if it's free, and the next, or this chunk to move forward if this is not free. Okay, you can try it for yourself. We actually now have a kind of nice README file, so you can know what's happening, and this is the GitHub link. So we needed a way to test it, to see how would our allocator compare to malloc. And what we did was this. Let's suppose we're in this first line here. We allocated like 512 big buffers. We said like, okay, a big buffer is 1,000,000 elements, in our case integers, and then we multiply that by a random number. So it's a big buffer with a random size, but it's big. Anyways, so, and then there are the volatile blocks. The volatile blocks are, we allocate 512 big buffers, and then we free 100, and then we create new random sized big buffers and allocate them again. So that's our basic process, and for the small number of blocks, we actually were able to be a little faster than the GNU library malloc, but you can see that when the number of blocks and volatile blocks increase, we actually end up losing by a wider margin. So we were humbled by this, and we saw like, okay, malloc must be really good at even with specific requests, because we were only trying to use big buffers here. I'm sure that if you use like small like classes and objects and stuff, malloc would be just tear us apart. So we decided to search a little deeper into malloc and the implementation with the GNU malloc. So the first thing we saw is that we can actually replace the C library allocator with your own. So if you think you can create a better malloc, you have the opportunity to use it in your C library. The only thing you need is to implement these interfaces. So you need a malloc, free, calloc, and realloc functions. These are simple to implement, considering what we already had, but we didn't really have time to do so, and we thought that our project was finished enough the way it was. And maybe if your program has like different types of allocator, you might need to implement these as well. Okay, so how does malloc actually work, right? the first thing is the data structure. Our data structure, as I said, we didn't really care about size, but here they do. And they have two different data structures, one for allocated chunks and one for free chunks. Here is the allocated chunks metadata. It's just a single space in memory with the size and these AMP flags. I'll talk a little bit more about A later, but M stands for if the chunk is M mapped or not, and the P stands for if the previous block is in use, right? And then we have the free chunk. The free chunk has the same initial structure, but it also has a forwards and backwards pointer, just like ours, to create a doubly linked list, right? So let's suppose there's another really smart thing about the free chunk. They also have a copy of their size in the last piece of memory. And why do they do that? Because if you had an allocated chunk, you can know with the P flag that the previous one is not in use. So if P is equal to 0, the previous one is free. And then you can just use pointers to go back a little bit, and you can get the address of the prev size. So you can actually go back to the beginning of the previous block. So you don't really need a linked list with the allocated chunks and the free chunks. And if P is equal to 1, the previous one is occupied. It's also allocated. So the second thing is the fitting strategy. As I said before, we used first fit. That is the easiest to implement and also the fastest. But they actually have a clever way to introduce this in a smarter fashion. So how are they doing this? They actually have the linked list sorted by size. So when you go through the linked list and you know your size, you just go forwards until you find that the next element is not big enough for you. And then you stop, and that's your memory. Here, we only made the presentation to fit the slide, but imagine that you had a bunch more of little blocks further down the line. If this wasn't sorted, you'd need to go through them all. So, they also have another smart idea. The next idea they have is they also have sometimes they have another pointer here, and this is for big buffers only. It's a new forwards and backwards pointers that point to the next one with the same size, with a different size. So here is that illustrated. So here in this big block, you have a pointer to the next size available. So you can even quicker jump this linked list to get to the size you want. And then you go to the last one and you get the same amount of memory. You usually you don't really want to allocate this guy because then you have to change all the pointers. So what you usually do, you go forwards until you find the last guy and you can allocate that. And so you don't have to mess with the big pointers, right? So this strategy essentially is a best fit. They find the best available space for that kind of memory. Again, if you had a bunch of blocks here in the beginning, you would skip a lot of processing time just by jumping to the next size. So, the third thing we have with malloc is multi-threading. With multi-threading, you can have multiple people trying to allocate and free memory at the same time. And here I'll explain the concept of an arena. An arena is a region of memory that you can, only one thread can use at a time. This is usually like an M-mapped region that you have available to your program, and only one thread can like allocate at a time or free. Just like in our implementation, we had a lock. Arenas usually have locks to protect them. So, unless malloc does this thing that's really important in programming, that's caching. So, it usually selects a few sizes that it realizes will be useful in the future and creates a vector with them. So before you even like start to go through the linked list I showed you before, you check the cached data to see if you have any blocks that will fit your needs, right? And this cache is a little special because it will only give you the memory if you have that exact size. So this little block, you won't. You just have to go through the list again. But if you have a precise amount of memory, then it will give it to you, and it's much faster because you only need to search through the vector. So, how do you decide which sizes will be in our cache data, right? Heuristics. So, yeah, it's just heuristics in my mind. It's just like a little magic you do to something that kind of works. Oh, okay, this works. Okay, it's heuristics, right? So it's just something that they realized that would really fit, so they went with it. So imagine you're trying to like allocate with dynamically allocated memory a bunch of classes, a bunch of objects, right? And they usually have like the same size because you're using like one class. So this allows you to have a bunch of cache data available for you when you want to allocate the next one. And this will make it really fast. So with multi-threading, if you don't find a T-cached space for you, you can also use, you have to wait in line with the other threads to use the arena of allocated memory. So malloc is smart enough to see when there are too many threads trying to access the same area. It kind of like goes through the line of all the threads trying to allocate or free memory in one specific arena, and it checks the pressure. So here you have an arena full of people, and when the thread pressure gets too high, malloc just creates another one. So now we have more arenas that you can use, and then you get a divided load between them. So the thread pressure doesn't get as high. So this is so we realized that malloc is so much better than what we did. They have like
B stands for what?
Oh, it's big buffer. But we call it, we gently gave the name baby malloc. So I'm sorry, I think I
Push the first button, I think.
I pushed the first button. This one?
No. Yeah.
Okay, great. Sorry. So, in the end of the day, we realized that malloc is a really thought out structure, and I think this guy, Douglas Lee, was a genius and probably had some kind of team working with him, and it's really good. and it's good for all use cases. Like if you're allocating small amounts of memory, it will usually all be in the T cache for you, so it will be fast. If you're allocating big buffers, you have an optimized linked list to use your big buffers with, right? So our baby malloc is just a small guy trying to understand this world of malloc and how it works. And that's the presentation.
Any questions?
Any questions? Yes.
Do you end up taking a look at other alternative malloc implementations that are out there that people use, like tcmalloc, jmalloc?
We actually looked a little bit, but then we were kind of overwhelmed with the initial malloc, so we were like, okay, let's get this one really good, and then now we maybe look at other ones and we can understand them better. But it's a good idea for the future.
Yeah, just out of curiosity, I've never really got into this part of malloc and these other projects, but I know that they exist. So
yeah,
it's in case it's interesting for you.
I think it's really interesting. I'll definitely check it out. Thank you. Anyone else?
All right, thank you very much. So next presentation is Debian image generator at 3 p.m. Okay, thank you.
By the way, here are some references you can get from our talk, so you can read up more about it. That's all.
Hi everyone, my name is Jadila. It's very nice to be here today. I'm a computer engineering student at the FSU de Minas, Poços de Caldas, Minas Gerais. And I work at Amora Dev with Ellen. And we came here today to talk about DevOS and how you can to customize and control your image, your package, your files, folders, and also customized services. And all this keeping the control above what will be installed in your image. Everything for several single-board computers.
Hi, I'm Pablo. I'm 22 years old and I study in FSU de Minas too. And we work together. I'm on dev with Ellen, so Ellen, thank you for your presence and your mentoring. As Jadila mentioned, we're here to talk about the open source project DevOS and how it's been important in our work. We can also talk about practical examples of its use and the importance in real scenarios, right? I like to say my English is not good, so I try to do the best of me, right? But so Jadila, can you start for us?
Sure. So first of all, let's talk about what is DevOS. DevOS, the definition of DevOS, is Dev Operation System Image Builder. So as its definition says, DevOS is a tool to build your image based on Debian operation system. This tool was written in Go language and uses a YAML file as a receipt to read and to build the image. You can know more about this project on GitHub. Okay, so now that we know what is DevOS, why should I use this tool if I can just Google image for Raspberry Pi or image for Orange Pi, or use an image of Armibian project or Haspibian. The idea of use DevOS is that you can define what will be in your image. That way you can save memory from resources that will not be used, and you can simplify your image, not using, for example, an interface. Besides that, when we talk about to build an image, we can mention other projects like Yocto project that was mentioned in another talk here. Yocto project is a project that can support other operation systems and enables a deeper level of configuration because works with layers, for example. But sometimes that level of configuration is not required. So with DevOS you can define what will be in your image in an easy way. You can easily see everything that you will do. That's because everything is written in a YAML file. That is a very readable file. Okay?
So is it like Yocto?
Looks like Yocto.
It's more easy.
But it's easier because with DevOS, I will exemplify with a YAML file. With DevOS, you can see everything that is happening in your image. So Yocto, you have to work with layers. They're kind of complex to understand and work.
Just for curiosity, something people know about DevOS? Oh, nice to meet you. Exclude any.
So here you have an example of YAML file. DevOS is based on actions. So we have a list of actions that you can run on DevOS to build your image. For example, we have here the overlays folder that contains everything that will be in your image. So here you define the folders, the files, and the packages that will be added to your image using the action overlay. You can also add some customized services and enable and start the services with action run. Here we have some parameters, and these parameters are very useful because you pass them by command line. So if you want to change the version of Debian, for example, you can just change on the command line. It's not necessary to go to the file and edit. So it's very useful. Another thing is that you can define a root password. So when you build your image, you have a root password to access your image.
And it's interesting to say, you can send to image the passwords for Docker containers, passwords for the application, SSIDs, network passwords, among other
parameters that are necessary. We have here just 4 parameters, right? But we can write on YAML file or send on line command, just type debs and send parameters, and it's easy, right?
Yeah.
I'm sorry.
No. And here you have the action apt action. That is the action to add packages into your image. So here you can define which package will be added, and that way, like I said before, you can save memory from resource from packets that will not be used. Dabos project is very nice because you create an image ready to use. So we could on our project take an image and edit the image with the folders that we want to. But with Dabos we have a ready to use image, so it's very nice. Here you have a list of other actions. You can know more in Dabos documentation. But all these actions are related with the control of your folders, your files, your packages, and also the operation system.
Oh, all right, so let's exemplify in practical use case how this tool can benefit us, right? Imagine you have an application running on single board computers, right? SBCs. And that application has a constant updates. So some clients can opt for plan X with some features, while other clients choose with different features. Okay. Consider that these clients might have various SBC models, as Raspberry Pi, Orange Pi, maybe others, why not? So with a few clients, it's easy to manage this data remotely, right? Just access on port 22 with SSH, but it's easy with a few clients. Occasionally to do the necessary maintenance if we have an error. But what about when we have 300, 400, or 500 clients? How you can identify a specific feature or service with some error to do the necessary maintenance, or to resolve some error, or to resolve these issues with fast, or to do it. With a multiple clients, it's a problem, okay? Change. All right, so various that can solve this problem and offer versatile control, but for the scenario, Dabos was the optimal choice. As I mentioned, we have Yocto 2 to generate the image, and we have EOS3 to have control about the image, but Dabos work so good, right? So to resolve this challenge, for every new feature implemented for specific clients, we generated a new custom image, right? This method offers a greater control over the client's features, depending the image installed on their board. Okay, so let's exemplify a little more, okay? Imagine you have 2 clients. Client 2 may have the same features as client 1 plus a few more, okay?
There's a presentation device there you can reach point.
All right.
And also to the next.
Just
No, up and down.
Up and down, and also
okay.
it has a laser.
Oh, thank you.
Check your
Take. If client 2 reports an issue with the new feature, we know that any clients using the image generated by Dabos on this day might have similar errors, right? This makes maintenance a lot easier, the true versus control, and easy to create a new image, because we know that all clients with possible errors with the new image generated by Dabos. Furthermore, Dabos has provided various other resources for our needs, as control over services during the image creation, before the image creation, right? It allows to resize the image after the boot to minimize unnecessary stores, among other benefits. But so Dabos, it's an amazing and incredible and versatile tool with various use cases. We have presented just one application for us, and crucial an application for us, but maybe some of you can find other ways that Dabos can help our needs, and it's very interesting, right? Last few months, for example, we need to control the boot files for Orange Pi works correctly, and DevOS helped us a lot, right? Jen?
Yes, we had a problem with TTI reading serial with DevOS, and we discovered that when we edit the HTC Linux file, we could resolve this problem. And so we add a service on YAML file, and the services was responsible to reboot the board and change HTC Linux for and this way we could read serial and resolve the problem that we had.
All right, it's more faster within Planet, but that's it for today. I would like to thank you for your presence and the opportunity to be here. So we have our GitHub links here, and so thank you. Thank you.
Any questions for them?
One thing that was clear for me, in Octo you can like apply patches to the packages, and you build the packages on your local machine. You build all the packages and build the distribution on your machine. Here we can apply in DevOS. We can apply patches to the packages, to the kernel, and build. Or the packages are just downloaded from the Debian.
Yes, the packages are downloaded. I don't know exactly how everything is done, but the big difference here from DevOS and DevOS and Yocto project is how everything is done. So with Yocto you works on a terminal and with layers, like I mentioned before, and with DevOS and you have the YAML file. I don't know exactly the answer for this question, but I guess that is downloaded. The package is downloaded.
You use the Bootstrap, right, for part of the root file system building, right? The Bootstrap will download the packages, so that's probably that. Also, I saw that you have interfaces for installing new packages or so, but the Bootstrap is not used for that part of the build root process.
Yeah, we have here on.
Okay, because when I see that file that you are showing us, all I can see is that you will enable some repositories and install some packages.
And here we just bring an example. Where we can do a lot of things and application more actions. So here we have just an example, but you can do more things.
Yeah, I think the real question is what else could we do using DevOps that we are not like usually able to do using the Bootstrap, for example?
For the Bootstrap, I can't answer exactly, but with DevOS you can pack some packages, download the package from your GitHub, for example. You can unpack and can run some commands that you could run on Bash, for example. You have a lot of actions.
Okay, that's
So you can like create a package like your GitHub repository and then build with DevOS into your image?
Yeah, you can.
Do you know if RIS-532 is supported?
I didn't understand.
Do you know if RIS-532 is
Oh, I don't know.
Are they supported by the official Debian repository?
They do have a 64.32.
So it's probably not because it gets directly from.
Yeah, but if you have an option to build it locally instead of just using that Bootstrap, it should work, right?
We could test this.
And yeah, so the second question, I agree that using Yocto, it's you go down the rabbit hole and so what's the level of control you have over the packages in this tool? So let's say that I want static libraries, but I don't want debug symbols. Can you specify this level of details in your image to generate?
I don't know.
We have a log console, right? With the
I don't know. I really don't know. I'm sorry.
So
I mean, if you're using that stuff, you probably can just set which packages you want.
Because the debug symbols are usually inventory the package, so you just don't know them. That's possible.
yeah, so you can, so if under the hood it generates a CH root environment, and there's an action that you can execute any kind of script. So you could go there and have a script that will build something or will change the package some way.
Yeah, but also, like, I think that disadvantage of Yocto is that it's supposed to be a push button work, right? So you just push a button and it should work. If I have to do a stage route and configure stuff, I probably just do it.
Some other questions? All right, any other questions?
Is it possible to bin package versions? For example, let's say you don't want to use the newest version of OpenSSL and you want 1.0, for example. Is it possible to bin?
To download a new version of the package.
Another version.
You don't want to update, you want like a specific version.
Just right here, right? FTP package.
Yeah, but how do you specify the version?
For packets, I don't really know because we can do this for the version of Debian. So you can define the version, specific version that you want. But now for packets, I don't really know about that.
I believe the syntax there is the same as Debian. So you just equal the number of the version.
So I saw you have the Origin Pi there and the Raspberry Pi. Do you maintain some images for us, some default themes, or no? Just curious.
We have some basic images that we construct on Pablo's GitHub. He has some images, and it's very nice because we use the same code, the same YAML file to build an image for your Orange Pi and Raspberry Pi. But we define the board on command line. And so we run different scripts for each one, so in the same YAML file. So we just change on command line which bird we want to create the image, and generate. It was not necessary go to the file and edit.
All right, thank you very much. We'll be back at 4 p.m. for the latest two sessions. First one on stateless decoders and the new AV1 kernel micro API, and the second one on how Bitcoin open source development works. There hopefully is a coffee break out there with coffee this time. So let's get back to 4 p.m. Thank you.
Ladies and gentlemen, my name is Daniel Almeida. I am with Collabra. I'm a consultant software engineer, and I'm here today to speak to you all about the stateless decoders and the new AV1 kernel UAPI. At some point, somebody said like micro UAPI, which is understandable because
I was the one.
Yes, because when you have like U, people usually read that as mu. But that's UAPI as in user space API. Sorry for this confusion. So to start off with, there are plenty of terms here. We have stateless, we have decoders, we have UAPI, and we have AV1. So it's a bunch of different terms and nomenclatures. So the very first thing I want to do is like break this thing down so that we can understand what's going on, right? So as I said, let's break this down. Starting with video codecs and what are video codecs and why we need them. So pretty simple, video codecs, they're needed because otherwise we couldn't have video. And our current form nowadays for a very long time, unless you have a very fast transport, like if you have a console and then you have that thing connected through HDMI, that's going to be one thing. If you have like something like a PCI bus, it's going to be another thing. But if you want to like store that thing on your computer, you want to have that transmitted through a network for the purposes of watching that on your television through a streaming service, then raw video is simply not feasible. If you do the math and you multiply everything, it's going to be a huge file. So we need video codecs for that. And for like, we're lucky because video signals, they're full of exploitable redundancies. And video codecs, they're the technology that take these redundancies and work to eliminate them, to capitalize on the fact that we can remove some information and arrive at a passable approximation, a result wherein people are watching it and they're like, oh, this doesn't look that bad or not noticeably bad. So video codecs, as I was saying, they're a technology that can compress and decompress raw video by capitalizing on the fact that video is a type of signal full of redundancies, and most of the time this process is lossy. So if you take, although you can have lossless, but most of the time the process is lossy. So if you take an input and you get that through a video codec, you're never going to be able to get the exact same output back. I don't know how many of you are aware of the needs more JPEG meme. So JPEG is like lossy as well. So if you have an input thing and you put that through JPEG and you do it over and over and over again, eventually garbage is gonna like start coming out. So most of the time the process is lossy, meaning not perfectly reversible. And the objective is to arrive at a passable approximation for the original and for a given bit rate and power envelope. So bit rate is the amount of bits per second that the encoder is going to be putting out. So it's pretty trivial to understand that if you increase the amount of bits per second that you're allowed to have coming out from the encoder, you can get better quality, right? If you increase your the amount of bits that are coming out, you can have better quality. If you relax your the power expectations for that piece of software, you can go faster, but then you're going to use more power. So the idea is to, again, have a passable approximation given a given bit rate and power envelope. The name codecs is, again, shortened from encoder/decoding. Encoder/decoder. And usually, a codec will put out a spec file, and only decoding will be standardized. So the idea is that encoders, they can do their secret sauce and magic and sort of innovate, so long as it decodes to a valid video as per the codec specification. All right, so we know what are video codecs. Let's very briefly talk a little bit about what are these redundancies. We don't want to waste too much time here. So the first type of redundancy we have is spatial redundancy, which is like the understanding that if I take a picture from any one of you guys in this room, probably the pixels that represent your shirt, they're going to be roughly the same color. The pixels that represent your skin color are going to be roughly the same color. The pixels representing the background are going to be roughly the same color. So it's the idea that if I want to predict a given pixel at a given particular place in the image, the best predictor for it is going to be the neighbor pixels, the neighbor pixels around it. We have temporal redundancies, meaning if you're taking, like video is a sequence of frames, right? So the idea that a given frame, the next frame will be the previous frame is a good predictor for the current frame, especially if you increase the amount of frames per second, because the more you increase the amount of frames per second, the less time will have elapsed, obviously. And unless you have a scene change, right? If I'm taking, like if I have a camera and I'm filming this part of the room, and then somebody else has a camera at that part of the room, and there's a scene change, and now the signal is coming from that camera, it's obviously, you'll have to reset the decoding process or the encoding process. But most of the time, you have a single camera for a given length of time, I don't know, 5 seconds, 10 seconds, filming the exact same thing, and very little difference will have elapsed, so you can use previous frames to predict the current frame. You have chromosome sampling, which is amazing, which is the idea that if I take a picture of this place and I reduce the amount of color information, you guys are not really gonna notice a degradation that's too big. When if I remove the color intensity, if I remove the luma plane, if I downsample the luma plane, you guys are gonna notice, because our eyes are more sensitive to changes in the intensity of light than to the, let's say, intensity of the color information, the UV plane. We have quantization, which is just a fancy name for division. So you're gonna, without getting too much on how video codecs work, you're gonna get an error term, then you place that into the frequency domain, and then you arrive at a matrix of coefficients. And if you quantize, which is again just a fancier term for divide, you can eliminate a bunch of coefficients. You can get them to go towards 0, and then you don't have to send them. That's the idea. And this is very lossy. So if you quantize aggressively, you lose a whole bunch of information. So it's one of the most important parameters for an encoder is how much quantization you want going on. If you have way too much quantization, you start to notice a degradation in the final image. You have entropy coding, which is again compressing using probability distributions, and we may have AI, which is I think one of the future directions that video codecs are going to. And okay, this is what video codecs are. That said, can we make this faster? Why do we want to make things faster? Well, if we have a hardware accelerator that can take the input and let's say decode, if that thing can decode a given video file without using your main CPU, that's good, right? Because the main CPU is going to be idling for a longer period. If that thing can decode video without heating up your laptop so that it's not scorching hot while you're on your couch, that's also good. Does anybody here like, having a scorching hot laptop on their lap? Nobody likes that, right? If that thing can save power, that's also good. So the idea is, if we have a hardware accelerator, we can go faster using less power most of the time. But there's a downside. I think there are two main downsides for like having hardware accelerators. The first of which is, if you have a hardware accelerator, unless you're using an FPGA, but if you have an ASIC, you cannot reprogram that in real time. So, and most like codecs, they offer different levels of service. Let's put it this way. Because you guys can imagine that if you're like, the requirements for like an IMAX movie theater are different from the requirements of me and you watching something on YouTube. So usually not all of the codec will be synthesized into hardware. People are gonna look like, go down like, what are the main features that people are using here? What are the main profiles being used? And we're only going to synthesize that subset of the codec into hardware. And if you want to use some other levels, like higher profiles with higher bit depths, well, you're not going to be able to because your hardware will probably not have support. So most of the time we have hardware acceleration for like 8-bit and 10-bit content every now and then. And the other downside is that now we need driver support, right? Because we have hardware to drive, so we need driver support. And we need an API because we have to communicate somehow with the underlying hardware on how we're going to operate that. It's not magic. It's not magical, right? We need to talk through an API in order to drive the underlying hardware. So just one more time, we need APIs to communicate with the underlying driver and hardware accelerator. So enter the world of video codec APIs, of which we have plenty. We have the XVA from the Microsoft Cloud, which stands for DirectX Video Acceleration. So mostly Windows, Xbox. We have VA API, which I think is the most famous API on Linux, which is what I work with, by the way, which was created by Intel. So if you have an Intel GPU or an AMD GPU, you're probably going to be using VA API. You have stuff from NVIDIA. If you have an NVIDIA GPU, NVEnc, NVDec. You have Vulkan Video, which is Vulkan for video. And you have video for Linux and so on. We could stay we could stay here for a long time just talking about video APIs. And why do we have so many? Well, some video codec APIs are more suitable for a given platform. Some other video APIs are more suitable for other platforms. Some are vendor specific. So NVEnc and NVDec are obviously only going to be used if you have an NVIDIA card. Some are more suited to abstract over hardware, video codec hardware that we find in GPUs, which is one of the major use cases, right? Like if you have an Intel GPU, that has a video codec accelerator inside of the GPU. And if you have an Intel GPU, again, then VA API is possibly what you're looking for. Same if you have an AMD GPU. But not all video codec hardware is within GPUs. So that's my main point. So these are like some of the reasons why we have so many APIs out there. How is the kernel related to this? Because if you guys will remember, this talk is about the new kernel UAPI for AV1. So we know what codecs are, so we know what decoders are, so we already know, some of the title for this presentation. And now we're gonna go a little sorry. Oops, wrong way around. So now we're gonna go into the kernel and what the kernel has to do with anything. So again, back to VA API. If you're using VA, VA is structured a little bit different. Most of the interesting stuff is happening in user space. So if you're using VA API, there is a component sitting in user space. If you're on Intel, that's going to be Intel Media Driver or Media Session. This is going to be a user space component. So your program will be communicating through VA API to this user space component. This user space component in turn will build a set of command buffers, which will tell the GPU how you're going to be performing this video decoding process. And then the kernel will be mainly charged with scheduling the jobs on the GPU and that kind of thing. So most of the work is done in user space for some video codec APIs. Other video codec APIs like Video for Linux do not have a user space component like VA API does. Most of the interesting stuff is taking place in kernel space. So, and this type of API, the client will be using a given API to talk directly to the kernel, not to the user space anymore. And the kernel will then program the hardware. And in order to talk to the kernel, we're going to be using a UAPI, a user space API, which is again an API, a contract between the kernel and the user space, so that user space can drive the underlying video codec hardware. So far, so good? Yep. All right. This talk, I've presented to you guys a bunch of APIs, right? The XVA, VA, blah, 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 blah. This talk is specifically about Video for Linux. What is Video for Linux? Well, Video for Linux is a API/frameworks for a bunch of multimedia devices out there. So DVB, tuners, radio things. I don't really care about this for the purposes of this talk. I'm mostly interested in the support in Video for Linux for video codecs, which is like the whole point of this presentation. So Video for Linux got video codec support as of recently. And when I say recently, it's like quote unquote because it's been there for like, I think stateful support has been there for like 10 years plus, kinda. So recently, but not that recent. And before we can talk a little bit about Video for Linux and how it operates, I want to talk to you guys very briefly about what's contained within the video codec bitstream. What is the result of an encoder? What the encoder puts out? So most interestingly, the encoder is going to put out the compressed data. That's the whole point. That's the data that you're gonna get and decompress, right? But that's not all, that's not everything. Another very important thing that an encoder is gonna put out is some metadata. And we need metadata because the metadata is the actual part of the bit stream that is going to be controlling the decoding process. So this metadata will be sent with the bit stream, and we'll use this metadata, the hardware will use this metadata to actually control the decoding process in real time. So again, the metadata controls the decoding process, may persist between frames. So we can have metadata that specifies a sequence. So like, okay, we're just starting the video playback. Here's some data that I want to persist for the entire stream, for instance. Okay, this is metadata that's going to be there for a long time. If any of you here are familiar with H.264 or HEVC, that's roughly SPSS, PPSS, VPSS metadata that's going to persist throughout the entire decoding of the stream. Or you can have metadata that's going to be related only with a given frame. And as I said, you have the slice or the tile data, which contain the actual compressed data that you're going to hopefully decompress. Okay, so I said this because before we can talk about video for Linux, we have to talk about the two different APIs that the Video for Linux subsystem offers us. So the talk of this presentation, again, is about stateless decoders. Why stateless? What is the term? Well, I said stateless because stateless is one of the ways that you can drive a video codec hardware accelerator. There's another API, which is the stateful API. And what is the difference between a stateful API and a stateless API? Well, the difference lies in what we're going to do with this metadata block. So in a stateful API, you can imagine the underlying hardware. It'll be comprised of a bitstream parser to extract that API, that metadata from the bitstream. It's going to contain a microcontroller in there running some firmware. And this microcontroller will take this metadata and use that metadata to sort of implement the control path, to actually control the actual decoding. So a hardware that has a parser within it, that has a microcontroller that can parse the bitstream, extract the metadata, and control the decoding process will be a hardware that we're going to be exposing through the stateful API. We can think of a stateful device as a black box. It takes in video data, and it does its thing, it does its magic, and we get data back. This is easy for the programmer because the programmer doesn't have to care as much. It's way less work for the people developing for that device. But the hardware itself is more complicated. You have to have, like, it's occupying more area in the die. It's more complex. Another type of hardware that we have is a stateless, which is, well, the actual opposite. A stateless device doesn't have a bitstream parser. It doesn't have a microcontroller, firmware running. It's just if I said that the stateful API is a black box where you put in data and the device responds with decoded data, the stateless API is the other way around. It's a clean slate where you push one more time, let's just go back. You push the tile data, and then you have to feed the metadata because the device cannot parse the metadata on its own. So okay, we know what a codec is. We know what a stateless decoder is. We know what a UAPI is, which is a contract between user space and the kernel. And now we just need to know what a codec UAPI is, and more specifically, what the AV1 UAPI is. So we need to pass the metadata. We have established that. And in order to pass the metadata, we need to parse that somewhere else, and the somewhere else is going to be in software. Because the whole point of this thing is not having the hardware do this job. It's actually having software to do this job. So we're going to be parsing that in software, and we need an API to pass that information to the kernel. And this API is known as the codec UAPI. So we have the VP9 UAPI, for instance, which is for the VP9 codec. We have the AV1 UAPI, which is the UAPI for the AV1 codec, which is the API that we're going to be using in order to pass the actual metadata so that the hardware can do its thing, can decode the data. Speaking of codec UAPIs, Collabora has been merging for the past, I think, 3 years. we have been steadily merging support for codecs out there. So we have merged the UAPI for H.264, which is very famous, although it's like 20 years old by now. We have merged the UAPI for HEVC. We have merged the UAPI for VP9, and we have merged the API for AV1. For the 4 codecs listed here, 2 of them are not open source, which is like H.264 and HEVC, they're not open source. And VP9 and AV1, they're open source. For the non-open source codecs, we have a problem. What is this problem? They're full of patents. And, well, if they're full of patents, this opens up the following scenario, the scenario of patent litigation, of charging fees so that you can use that in your computer, charging a fee per file that you encode or decode. And that's, kind of bad. So let's recap what we know so far. A video codec compresses and decompresses video. We need that because raw video is simply not feasible in 2023. We need APIs to talk to the accelerator because we want a hardware accelerator to use less power and to be more efficient, to be faster, to free up the main CPU. This presentation is about the Video for Linux subsystem and how we can use Video for Linux to drive these accelerators. In Video for Linux, we have both stateful and stateless APIs that can drive different types of devices. We've seen what a stateful device is, what a stateless device is. For the stateful API, we send the entire thing as a black box. The device does its thing, magic, boom. For the stateless API, we send the bit stream, and we must also parse the metadata in software and send the metadata separately through an API that we call the codec API. And Collabora has been merging these things into the kernel for 2 or 3 years. So far, so good. I hope so. Awesome. Let's continue. Why is this important? There's this research that was done by Cisco that everybody sort of cites this thing. All the presentations, I hear the same piece of information, that by 2022, Cisco had predicted that 82% of all consumer internet traffic would be video data. People watching stuff on YouTube, people watching stuff or like watching video content on their phones, on their laptops, and a lot of this content will be consumed through like your mobile device. Your mobile device will probably be connected through 4G, 5G. These things are not unlimited. There's usually a cap on the amount of data that you can use. You don't want to go through all of your data at once. And on the other hand, so we want to limit the bandwidth, right? We don't want to use all the bandwidth for obvious reasons. But on the other hand, there's a pressure for increasing the bandwidth. Why? Well, because we want higher and higher resolutions. Now there's a 4K if you're purchasing a television. I don't even think they sell full HD TVs anymore. So 4K is the bare minimum. You have 8K sort of creeping up. Hey, I exist. You have like HDR, which now needs 10 bits or has always needed 10 bits in order to decode. And these things, they drive up the bandwidth requirements. So they're two competing forces. So video is pretty important. I think we have pretty much established that. What happens when the technology that is underpinning video encoding and decoding is full of patents? Well, this happens. We have patent litigation between different industry members, people fighting each other over who should pay whom. We have a new concept, which is the concept of patent pools. Because previously in H.264, you would license everything from a single entity. HEVC innovates in which you now have to license things from multiple entities. We have pools from which you have to license patents from. This is bad. And we also have royalty fees that you now have to pay, which means like paying a amount of money just for the privilege of encoding and decoding using their proprietary codec. Like HEVC, I think, charges per file, and I think it's usually on the vendor. I think the vendor is sort of paying for this, but like it's there. Somebody has to pay for it. Unlike the free codecs. So for VP9, for AV1, no such thing. You don't have to pay for the privilege of using them. And this seriously hampers free and open source support, right? Because let's say if you have FFmpeg, which is free, everybody can download FFmpeg on their machines. And now you're like, well, if you really want to use HEVC and FFmpeg, you have to to pay. How is this gonna happen? Because FFmpeg is free, so it sort of precludes free and open source software support. And just as a curiosity for you guys, this is the patent landscape for HEVC. So you have multiple patent pools. So you have multiple guys, multiple entities that you can license patents from. You have people fighting over patents. That's not good. Enter AV1. What is AV1? Which is the last piece of the puzzle, if you remember from the title of the presentation. That's the only thing left for me to speak about. What is AV1? AV1 is the guy that came to solve everything. All these problems with patents, with people fighting each other, and with, most importantly, with people charging for the privilege of using their codecs. So AV1 is a state-of-the-art video codec. It's not only for video. You have a VIF, which is like the JPEG equivalent, so AV1 for images. It's built on top of VP9. It uses also parts of Daala, which was a codec developed by Mozilla. VP9 was developed by Google, or rather Google purchased the company that was developing VP8 and then VP9. It's developed by a consortium, AOM, Alliance for Open Media. So this is better, because this consortium is just big tech, big companies like Netflix, Google, Apple, a bunch of big players coming together and say, hey, you know what would be great? If we wouldn't sue each other for patents because we're all interested in multimedia. What if we got together and we came out with this thing that's free for everybody to use? And there's an agreement. If you don't sue me for your patents, like, I'm not suing you for my patents. It's an agreement where nobody's sued. How interesting. So it builds on top of VP9. It was developed mainly due to the uncertainty with HEVC, because people saw the scenario with patents in HEVC and they were like, oh, that doesn't look good. And most importantly, the hardware implementation, mostly for decoders, but also encoders, it's starting to ship. So you can purchase a computer with an AV1 decoder today, and with an AV1 encoder, if it's a brand new, I think the latest Intel GPUs also ship with the AV1 encoder, if I'm not mistaken. The latest NVIDIA chip, so if you purchase the 40XX series, so 47, 4080s, you also get AV1 encoding. So hardware accelerations is starting to ship. And it was developed by AOM, this Alliance for Open Media, which is non-profit, open, royalty-free, and provides multimedia technology. Members have dedicated the patents, and most importantly, they came up with libaom, which is the reference implementation for the codec. Now, libaom works. It says what AV1 is or isn't, but it's not the fastest thing around. If you want something which is fast, then you have other options. You have the Intel encoder and decoder, which is SVT. You have a bunch of other projects. Notably, you have David and Ravi. And AOM funded David development, and they wrote Ravi and in Rust, by the way. And these two things, they're meant to be fast. They're meant to be the pieces of software that you reach to when you want to do AV1 encoding or decoding in production. They're fast. Awesome. These are some of the members. So we can see like Amazon, Apple, ARM, NVIDIA, AMD, a bunch of companies. And as we said, if you want to drive a AV1 decoder, a stainless decoder, we need a AV1 UAPI so that we can pass the bitstream metadata, if you recall from some slides ago. And I've been talking over and over and over about UAPIs. I usually do not bring code into my slides, but let's just, for the sake of clarity, what is a UAPI? What does this thing look like in practice? So I have copied and pasted some of my code in here. So this is like, you guys can see that it's just a bunch of structs in which you put a bunch of data in, and then you send these structs to the kernel, so that the kernel can access these structs, the fields, and then copy these values into the hardware. Because the hardware will come with registers, and then you're going to be copying the data from these files that user space has provided the kernel with, and you're going to be using the values in here to actually to copy them into hardware registers so that the hardware can do its thing. So this is one example for sequence metadata, which is sent like usually only once per video stream. We have some example for frame metadata, which is sent on every frame. So for sequence metadata, what is the profile? what are some of the features that are enabled or are not enabled? So like, are we using 128 times 128 super blocks? This is optional. So this thing will have a bit which will be set if this feature is being used. If any of these features are being used, is the content monochrome? Are we using a feature of AV1 called restoration? Are we using super resolution? So this will all be into this flags field, and we're going to be using that to program the hardware in the kernel. For the frame, what is the size of the frame, right? What is the resolution, the height and width? What is the ID for the current frame? What is the set of all the frames that this frame references? Plus a bunch of other information that we need on every frame in order to decode that. Again, where do we get that? We parse that from the bit stream. Who's parsing this? Some other software like, say, GStreamer in user space. Because we don't want to parse that in kernel. Also, I have to say this. We don't want to be parsing the same kernel space. Why? Because we don't want to write parsers in kernel space. It's a security liability. We have some per tile metadata. So anyhow, just metadata that your user space is filling, and it's passed into the kernel so that the kernel can use that to program the device. This is one excerpt from the AV1 parser in the streamer. So this is just the streamer going through the bit stream and reading a few bits at a time. And this is like kind of copy and paste from the kernel, from the codec spec. So the codec spec says how you're gonna parse it. So this is like what the streamer is doing. Like they get the spec on one side, and then they're like writing the same code that implements the spec so that they can parse it. And the streamer will be eventually filling the video for Linux structs, the UAPI structs. And this thing will eventually end up in the kernel, where the kernel driver will be using the values that user space has passed in to write registers and the actual device so that the device can decode. And what is the hardware that we support so far? Currently, we support MT8195, which is a MediaTek SoC that's used in some Chromebooks. We also support RK3588 from Rockchip. There's a driver for this from one of my colleagues, Benjamin Gaynard. So he merged support for this in the kernel. And unfortunately, thus far, these are the only two hardware that we support because there's not a whole bunch of hardwares for AV1 out there. So all in all, these are the only two hardwares that we could get our hands on and use them to develop drivers for. So just a summary, because I want to wrap up over here. AV1 is a state-of-the-art codec. Hardware support is coming out. It was developed because there was a huge uncertainty in terms of patents for HEVC, which is the newest codec from the MPEG guys. Collabra has merged support for AV1 stateless decoding into the kernel. We merged a driver for RK3588. We merged the user space support into streamer. And, oops, sorry, wrong button. There's only two video IPs that we currently support because, again, these are the two hardwares that we could get our hands on so far, that we know that exist and that we could use in order to develop. But if new hardware comes along, they're going to be using our UAPI, and thus development time will be significantly faster. This will hit Chromebook users first. So if you have one of the most recent Chromebook devices, you guys are going to be using our code in order to decode AV1 video in Chrome OS. But more people will be impacted when new hardware and driver come along because they're going to be using our API to do so. And this is what I had to say. Hopefully it wasn't too confusing.
So what is the relation between VA API and this AV1 API? Does it use that?
No.
It's completely different?
It's completely different. So VA is, as I said, there's a user space component. This user space component will be talking to DRAM. It's another subsystem.
Okay.
And it's talking to DRAM because the actual hardware is within the GPU. So it's using the DRAM facilities to start communicating with the GPU. So it's entirely separate.
Okay.
For questions? I don't bite.
Just out of curiosity, is this related to your work with the video for Linux support for Rust?
It's not directly related, but I have a dream that one of these days in the future, and hopefully when I'm not too old, I'll be using there was support in Video for Linux to write codec drivers. But that's totally into the future. It's politics. You have to convince people. It's a little bit too far out into the future. But no, not today. More questions? Questions?
Yeah, I will still pay royalties in this case, right? Because you have let's call this a consortium between companies. They agree in not sue each other, but the final product will come into my hand with royalties to use that product.
No, that's the entire point. They agree to not sue each other, and they also agree collectively to not charge you.
For everyone, right?
For everyone.
For everyone.
Yeah. If you're using the MPEG stuff like HEVC, VVC, then you're out of luck. But if you're using AV1 or VP9, that's the whole point. Like, let's not charge the user as well. Because Google is not interested in you paying. Like, Google is already pretty rich. They're interested in you using AV1 to watch their content, for instance, on YouTube. Companies want you to be able to decode for free because it means that you can use that to consume their products. Like YouTube, for using Google as an example. Hi.
I recall that, so the lead camera projects about cameras, but I recall something that they were trying to handle the codecs. Do you know something about it?
That lib camera is trying to handle codecs. I never heard about it. I think the only support that we currently have for stateless decoders was written by Nicolas Dufresne from Collabora, and it's in the streamer. So I am unaware. I don't think so. More questions? Hi.
So when I use VLC, not paying anything, with some time or?
I didn't hear.
When I use VLC,
Yeah.
I'm not paying anything, and I'm playing those codecs, those proprietary codecs, and I'm doing some crime.
I don't think you're doing some crime, but what to say about the people developing VLC? So I don't know if you have noticed, but I think Fedora pulled out support for a bunch of codecs from Fedora, and that's the whole thing. Like, it's like a hot potato that people are like throwing around. So who's like having their hands on the hot potato? So like Fedora people are like, ooh, not us. Maybe somebody else should take the responsibility. And if you want to do this on your own and you sort of enable that on your device, So yeah, that's the situation.
Yeah, I mean, if you work for big companies that are usually worried about legal issues, they will not allow you to install VLC in your machine because of this. I mean, I worked for IBM and VLC was prohibited inside IBM. Just to give you an example, right? I know a bunch of other companies that prohibit the usage of VLC because VLC breaks patents and they're not paying for that. So it's a huge liability. One thing is, if you use VLC in your personal notebook, it's very difficult to sue you because it's difficult for one of these consortiums that are getting the royalties, fees, to find a user. But if you are a big company, you are an easier target, right? So it's easier to sue you, a big company in this case. However, I have to warn you that, at least in Europe, there are people that are being sued because of, not exactly because of this, but for instance, for piracy, right? If they download films from torrents or that kind of stuff, they are going, they are trying to find the person. So, it's always a liability.
Serpro, the national company, use VLC normally without problems. And we had a great thing. I think it's not, it's in disclosure, not totally true.
And VLC is available on Google Play.
Sorry?
VLC is available on Google Play. You can download it.
Oh yeah, sure. It's just
So
an application.
Google pay something.
No, because VLC is not a Google app. So it's the.
But it's getting distributed by Google.
No, that's not the same thing. I mean, the company building the application is responsible for the source code. It's not Google. Google is just a store, right? So they are not paying any fees or getting any liability. So it's just like, if you go to, I don't know, to a retail store and buy a TV, a smart TV, it's not the retail store that is responsible for what is inside the TV. It's the company producing the TV, right? Now, the other aspect about VLC is that if you take a look at the VLC packaging, they separated everything. So you have the VLC core and the codecs, they are not part of the VLC package, right? So for instance, in Fedora, you still have I think you still have VLC as a package in Fedora, but the codecs, they are not available. I mean, you just have open source codecs in Fedora and without patent issues. The other codecs you usually download from RPM Fusion, for instance, and then even inside RPM Fusion, you will see that they separate these things into good codecs that they think they might not generate liability, and bad codecs, which such as MPEG stuff that can generate liability. So I don't know if Serpro allows all the codecs to run, for instance. I mean, I don't know.
I don't know either.
It's the same for GStreamer, by the way. So GStreamer, there's GStreamer good,
exactly.
GStreamer bad, and GStreamer ugly.
Exactly.
And if you install GStreamer ugly, ooh, you're in your own. It's a hot potato all over it.
Exactly.
Any more? Hi, again. Yes.
So there is this driver called vycodec that emulates in software a codec so we can test the API. I recall there was some patent issues. That's why Hans came up with this paper with
Another transform.
just for testing.
Yes.
And since you mentioned AV1, do you think that AV1 regulation could be implemented? Or I didn't got if the patents there is no patent on it, it's free, or if it's just a matter of these companies agreed that they are not going to use the patents for something bad, but the patents still exist.
You could, if you wanted to, but like FWHT, which is what is used in vycodec, is very small. AV1 is anything but small. AV1 is a huge production grade software. It's huge, so that we can compress better. You could, if you wanted to. I think Google gives away I don't know if it does for AV1, but it does for VP9. It gives away the HDL, the Verilog or whatever code for you to implement your own hardware decoder.
Yeah, and I don't know if this. I mean, if you look at when you showed the AOM alliance, the companies, right? I mean, some of them are giving the patents away for open source projects, right? So I know because of IBM when I worked there, so they decided to donate a huge number of patents to open source projects. So that means that they are promising they are not going to sue you if you are infringing one of their patents, as long as you are using open source, right? So maybe everyone has some patents or is using some patents from these companies, but they agreed that they will allow them, open source projects to use that without any legal issues. So
can they change their mind?
That's very difficult. I mean, it's very hard to do that, I suppose. I mean, it would, I don't know. I mean, yeah, of course, probably. But it's an alliance, they probably have contracts to be part of this alliance. It's not that easy to just say, I don't want that anymore, right?
Plus, it's the whole point, right? If they didn't want to share, why did they get into the alliance in the first place?
Exactly,
Hi.
Do you want to say anything else?
No, yeah, go ahead.
I feel like you could say that stateless versus stateful decoders are analog somehow to RISC versus CISC paradigms. Is that correct? Like, I mean, you don't depend on state, and you try to use less die in the decoder and everything. Would that be a fair analogy?
Maybe I've never thought about it in terms of CISC versus RISC, but the whole idea is to use less die area and shift away some of the responsibilities to the programmer and arrive at simpler hardware. I think we're running out of time. I just want to say before I go, I'm Daniel Almeida. I work with video codecs, if nobody has realized. I work on Chrome OS virtualization for video codecs, so video codec virtualization in Chrome OS for people running Android apps. So it sort of uses the underlying hardware in the Chromebooks. I'm also a Video for Linux contributor. I have been trying to merge Rust support for Video for Linux. That has been going somewhat well, somewhat not well, we'll see. But anyhow, I've been trying to. And I also do streamer development. So yeah, thank you. Thanks for the opportunity.
We'll be back in 10 minutes with how Bitcoin open source development works.
Okay, let's go. I move on to other things. It's in good hands with everyone. How Bitcoin open source development works. So first, my name is Bruno. It's my GitHub, Bruno ERG. I am an open source developer working on Bitcoin Core and director of education at VTUM and master student University of São Paulo. First, this talk is not about Bitcoin by itself. It's about its development and what we can learn. So let's start. Early 2007, Satoshi started working on Bitcoin. And we don't know who is Satoshi, if it's a single developer or a group of developers. We really don't know. But in 2007, we know he started working on Bitcoin because of some emails that we have. And 1st November 2008, Bitcoin white paper is published. So he published the white paper, and if you read the white paper, you realize that it's not so academic. And there are some mistakes compared to the protocol. So if you compare the Bitcoin white paper with the protocol, there are some difference. So it's okay. But in November 2008, he released the white paper. And January 2009, Genesis blocks mined. So blockchain is chain of blocks, of course. Genesis block is the first block. So in 2009, he created the first block. He mined the first block of Bitcoin blockchain. And 2009, January, Bitcoin version 0.1 is announced. So he released the white paper and released the source code, the first version of the source code. And you can read the first source code. It's not good. Definitely not good. But he wrote that and released. And it was Windows only. So it works, this first version only works in Windows. However, January 2009, version 0.2 is released. Marty, new developer, added initial support for Linux. And there were other new features like include mining on multiple CPU cores and initial Tor proxy support. So first version, Windows only. Second version, we had initial support for Linux. That's so important. Okay, July 2010, we have version 0.3. And you know the Bitcoin pizza guy that bought 2 pizzas for 10,000 Bitcoins? Yeah. So he's developer and added support for macOS in version 0.3. So of course, he's known because the pizzas, but he collaborated a lot for the project. So he added support for macOS, and we had other new features like JSON RPC interface and a new demo mode. And some users contributed translations into German, Dutch, and Italian. So first version, Windows only. Second version, we had Linux port. And third version, we have macOS. And July 2010, Bitcoin version 0.3.1. It was only a version with some bug fixes. But what's important, we had a new developer working on the project. Gavin Anderson. He started contributing to Bitcoin in July 2010. This is important because Satoshi started the project, then we had the Bitcoin pizza guy, and now we have Gavin contributing to the project. And July 2010, we also had Bitcoin version 0.3.2. Satoshi Nakamoto added checkpoints as a security safeguard that lock a block height to a specific hash. It's basically a security measure for Bitcoin. So he added checkpoints at this version. Okay. And in July 2010, we had the first consensus change because Bitcoin is a protocol, right? So Bitcoin Core is a software that implements that protocol. You can write your own software. You can write Bitcoin in
Rust, for example, you just have to follow the consensus. You just have to follow the protocol. So we have rules. For example, block size, how to validate a transaction are general rules. But Bitcoin is a protocol. It's not a software by itself. It's a protocol, and you can implement your own version of this protocol. And this July 2010, Bitcoin version 0.3.3 had the first consensus change, because if you read the white paper says that we follow the chain with most blocks, or the longest chain. And this is not true, because we follow the chain with most accumulated work. So if we have 2 blockchains, which one is the valid? How can we compare them? Basically checking the proof of work. Which one has more accumulated work? So July 2010, they changed the code to follow the chain with the most accumulated work, not the longest one. This was an amazing, a great and big change. And August 2010, we had the first critical overflow bug in Bitcoin, or better, the first critical bug, the overflow bug. And that was funny because someone was able to create millions and millions of coins. So Satoshi Nakamoto wrote the white paper and said that we have only 21 millions Bitcoin, right? But someone was able to create millions and millions and millions of coins. Why? Because overflow. It's an overflow bug. When he created a lot of outputs. So outputs is basically I'm sending Bitcoins for you, this wallet. So this address, for example. So we have a lot of outputs. We have a lot of outputs. But when we sum these outputs, we had an overflow bug. So he was able to create lots of coins because of that. And Satoshi had to fix this bug and tell users and miners to reorg the block with the overflow transaction out of history. So we had to rewrite the blockchain basically. So okay, this block is wrong. We have to redo this chain. So this is important in the history because we had the first critical bug, and it was really important because we want to have 21 million Bitcoins, and that's it. And someone was able to create millions and millions of coins because of this bug. In December 2010, development moved to GitHub. So now we have the development in GitHub. You can find github.com, Bitcoin. You can read the source code. And in 2011, we had the last contact with Satoshi. Satoshi wrote, I've moved on to other things. It's in good hands with Gavin. You remember Gavin that I said previously? Gavin and everyone. So he created the Bitcoin, he wrote the first version, he wrote the white paper, and then he realized, okay, I've moved on to other things. It's in good hands with Gavin and everyone. He said, basically, it's in good hands with the community. Move on. I'm out. And we don't know who Satoshi Nakamoto is, right? So it's basically the creator of Bitcoin doesn't touch the code anymore. Okay, so what can we learn? We are talking about open source development, and what can we learn? Talk shit, show me the code, right? So Satoshi released the first version of the source code along with the white paper. So sometimes people says, okay, I have an amazing idea. This is my idea. No. Do you think your idea is great? Code it. Show me the code. Satoshi had the idea and wrote the code. And if you read the code, of course, the code is not good. Definitely not good. So there were a lot of weird stuff, but he did it. This is important. He validated his idea because he had the idea, he wrote the white paper, and
he wanted to validate his idea. So he wrote the source code and released for us. Second, community support. Satoshi, in my vision, he wasn't a good programmer. He didn't know how to fix some bugs. Really didn't know. A lot of bugs, a lot of questions. What if? What if? What if? He didn't know how to answer, but a lot of people from the community knows, and the development moved with those people, and no one got paid for the development, no VC or funding. So he basically released the first version, and people were getting attention, and okay, this sounds good, let me contribute. Oh, this sounds good, and I think there's an error here I can fix. So this is how the Bitcoin open source development started. And what happened from 2011 to 2014? I said no one got paid for development, so Satoshi didn't get any money for that. Someone says, Satoshi has millions of Bitcoins. Okay, but if you analyze the blockchain, he never moved that coins. Never moved. There is a guy that says, I am Satoshi Nakamoto. Really? So, sign a message with the keys of that millions of Bitcoins that are locked. And he's not able. But he sued the developers because of it. And this is sad. But 2011 to 2014, Chaincode Labs founded. So Alex Marcus and Suhas found Chaincode Labs in 2014 to create a place for engineers and scientists to support the development of decentralized digital currencies. Blockstream founded. So Adam Beck is the creator of Proof of Work. Do you know Proof of Work is the consensus algorithm for Bitcoin? But Proof of Work is not a Bitcoin thing. Proof of Work was invented for emails to avoid spam. So to avoid spam, you had to Proof of Work to whatever. So he created Proof of Work at Beck and got involved with Bitcoin development. Matt Corallo, Greg Maxwell, Peter Rilla, they found Blockstream and released their sidechains white paper. So now, at that point, we have companies supporting Bitcoin development. This is good. Alex Marcus and Suhas, if I'm not wrong, they created the automated trading in USA. They created a company about automated trade algorithms. The idea they created, their company becomes so big, and they realize, oh my God, I'm playing with business. I'm not a coder anymore. So they founded Chaincode Labs to touch code. Okay, so we have these two companies. Chaincode Labs already exists. It's in New York, and Blockstream as well. And from 2020, we have development grants for Bitcoin projects and individual contributors. So Satoshi Nakamoto started Bitcoin without any money, but now we have a lot of companies and individuals supporting Bitcoin open source development. So for example, if you work on Bitcoin Core or other project, if you do a lot of contributions, you can basically say, okay, I want to work full-time with this project, and then you can get a grant with these companies like BitMEX, Square Crypto, now it's Spiral, OkiCoin, BTC, Kraken, the Human Rights Foundation. Human Rights Foundation support the Bitcoin development because they believe Bitcoin is important for human rights. Paradigm and Coinbase give out development grants to Bitcoin projects and individuals. So, for example, I work full-time on Bitcoin Core. Bitcoin Core is the same software that Satoshi wrote. So, of course, a lot of prepays, a lot of new code, new features, so it's not the same, but okay. So I work full-time on Bitcoin Core, and I have a grant, so I receive money to work on this project, and no strings attached. So I decide what I want to do, what I want to code, what I want to change, whatever. And I work mostly with QA stuff, basically fuzzing, no fuzzing. Bitcoin Core is also in OSS Fuzz from Google. And Satoshi created Bitcoin Core. So Bitcoin Core is a software, Bitcoin is a protocol, but there are many other Bitcoin open source projects. So BTK in Rust, Rust Bitcoin in Rust, of course, BitCD in Golang, and today Bitcoin Core has 911 contributors. So he started the project with Alon and with only Windows support, and now we have 911 contributors. And of course, Bitcoin is complex, right? We have a lot of different areas. For example, we have wallets, so we have to build transactions, we have to touch keys, we have to sign transactions, but we also have, for example, P2P, so network. We have the QA stuff parts, for example, we have functional tests in Python, the code is C++, but our functional tests are written in Python. We have, for example, mempool, so a lot of areas. And what do you think that Bitcoin Core as a free and open source project needs most? Now we have a lot of contributors, right? Now we have a lot of new features, now we have a lot of stuff. Satoshi Nakamoto created Bitcoin alone, basically. So he created the first version, but now we have money. Now we have grants, now we have developers working full-time on Bitcoin. We have developers from that worked previously Google, Microsoft. For example, we have Rusty Russell, creator of IP tables. He works on Bitcoin. We have, for example, Vasil. Vasil worked for years in MySQL and FreeBSD. He works on Bitcoin Core. And what do you think that Bitcoin Core as a free and open source project needs most? And I think this is not only a problem of Bitcoin Core. I think this is a problem that a lot of open source projects have. Why? What do you think that we need most? Test and review. Because coding is nice. Everyone wanna create new features. Everyone wanna have basically a lot of commits. But we need people testing and reviewing. Because we have a lots of open pull requests. And we have great projects into Bitcoin Core. For example, we have a project to encrypt the P2P layer. But I can develop it alone. But we need testing and reviewing. This is important. And when we talk about open source funding, specifically about Bitcoin open source funding, we have to change our mind. Because writing new features is important, but we have to evaluate testing and review, right? Because it's important. If you write a new feature, it needs lots of other developers testing and reviewing that. And when we have a release candidate, we need a lot of people testing that, right? So what we need the most is testing and reviewing. We have a lot of projects going on. We have a lot of open pull requests, but we have few people working hard on testing and reviewing. And when I say, for example, testing and review is not only LGPM, okay, right? No, it's really testing and really reviewing commit by commit and testing in different environments. For example, because we care. We want Bitcoin Core running FreeBSD, Linux, Windows, so we want to test the features in every OS, for example. So testing and review it's very important, and we have lack of reviewers. And I think this is not only a problem of Bitcoin Core, it's also a problem of other open source projects. And some final thoughts. Bitcoin development is community driven, so we don't have a leader. We don't have Satoshi Nakamoto never appeared again. we don't have a great leader deciding, do it, do that. No, it's basically community driven. So we don't have a great leader like, this is good for Bitcoin. We realize that Satoshi Nakamoto's appearance, it's important for the project because we don't have someone to depend. So it's basically so important. So nowadays it's basically community driven and we have a lot of projects involving Bitcoin, a lot of open source projects. And have an idea, just code it. Things will happen naturally. Because sometimes we have an idea and think, oh, I need money because I quit my idea. No, code. Code and things will happen naturally. And Bruno, I want to be paid for Bitcoin open source development. Start coding, start contributing, start reviewing PRs, and things will happen naturally. Most people, a lot of people fail trying to get grants because they join the project thinking about money. This is not the mindset. You want to contribute to the open source environment and things will happen naturally. So we check the projects. Oh, there's a guy working hard on project X. Okay, let's talk with him. Does he need the money, grant? Let's talk. So first we need the proof of work. And coding is nice, but testing and reviewing is super appreciated and a nice way to contribute too. There are lack of reviewers. This is true. A lot of projects need reviewers working hard on reviewing, of course, right? And basically, I said Bitcoin Core, for example, is complex. It's written in C++ and it has different areas. So wallet, P2P, mempool, and other ones. And of course, I don't know 100% of the code. I don't know about everything. I try to focus on an area, and this is important. So I focus on QA stuff and wallet and P2P, for example. And there are other people that knows a lot about wallets, but don't know anything about fuzzing, for example. So this is normal. You realize the project is big, but you don't need to be an expert in everything. Well, this talk is not about Bitcoin itself, it's about its development and what we can learn with that. I hope you learn a little bit about. That's it. Thank you.
Any questions for Bruno?
What's a side chain? Wasn't one of yours?
Sidechain is basically to have other blockchain linked to the Bitcoin blockchain. It's the idea of having a other layer into Bitcoin blockchain. This is sidechain basically.
You mentioned before that there was a bug with overflowing and a lot of blocks were generated. And then you, like Satoshi and the other guys, reverted this. How would this happen like today if something like that happened? Who has since it's a distributed system, is there any way of like reverting something because of a bug or something like that?
No.
Right now, it won't be impossible. It would be possible, right?
Impossible.
How did they did that in the past? I mean, they reached a consensus, and the other guy who did get all those blocks just, well, it's okay, I give up.
Yeah, there were a few people mining and playing with Bitcoin. Then, okay, guys, download this code and revert this block. But nowadays, it's not possible. It's impossible because of proof of work and other consensus things, so it's really impossible. So a critical bug can basically kill the project. So that's why we have...
Yeah, you need a lot of testing.
Yeah, a lot of testing. That's why I said we need testers and review.
Well, probably, I mean, if something, catastrophic happens today, what they will probably need to do is to fork the big Bitcoin chain, right? And say, this new chain starts at this block. And if you are using this old one, we are not going to accept that. But I mean, it will depend on how many people will jump into the new chain. Right?
Yeah, you have to need consensus.
Yeah.
So you have to convince people, okay, this new chain is developed one, let's move on.
It's why there's several crypto coins today.
Yep.
It's a very big responsibility there. Then, so if someone in your group messes up a code, there will be a lot of angry people at you. So yeah, you need a lot of testing.
Yeah, we need testing, reviewing, and we have lots of maintainers. So for example, we have today 6 or 7 maintainers because Satoshi Nakamoto gave the key of the source code to Gavin, but nowadays we have, Gavin is not in the project anymore, but we have other maintainers.
Well, not a question regarding specifically about development, but in general, have you heard about the official Brazilian digital currency that the government start discussing?
Yeah, Drex. Yeah, Drex. It's not a cryptocurrency, it's basically a MySQL or Excel, so it's not centralized, it's basically a private blockchain, they say. It's a private blockchain with their own rules and they control the project, so it's not open like Bitcoin that no one can change anything. But it's good because it's good, the idea, not the execution, because I don't fully agree, but the idea is they can write smart contracts with the money. So we'll have the real digital. So we can write smart contracts for your money, for example. And smart contract is basically programmatically writing conditionals for your money. For example, in Bitcoin, you can lock your coins for years. So, okay, I have a Bitcoin and I want to write a contract that I can only move this Bitcoin in 2032. You can do it. So you can play with, you can touch your coins programmatically. So this is the goal with Drex, that they want to create the real digital, so it's possible to write smart contracts on this money, but they can freeze your money and they can control your money. So yeah, I'm not a big fan, but this is being.
Well, they can do that today as well. So
yeah. So my opinion doesn't matter. Yeah, my opinion doesn't matter.
But that's different.
With Rex, it's a centralized switch to do that.
Well, yeah, but they can just do just as like Collar did, right? Write a law and then you don't have your money.
There are several banks to
or it's a different situation because with Drex, suppose you are a Bolsa Família user, and they give you the money, your Bolsa Família money, and that money you can only use on some circumstances.
Yeah,
For
I know.
example, buy food, buy gas, and just that. You cannot buy a new television for your home.
Yeah.
That's the idea of the smart contract.
Yeah.
The name Drex is funny. The X is for futuristic theme, It's a mess.
Yeah.
It's not your money anymore.
I think it will be Hyperledger. So they have a private Hyperledger with some nodes they control and they decide the rules and that's it. And we will have the real digital.
You mentioned fuzzing. How does fuzzing fit in the Bitcoin project?
Oh, nice. It's basically fuzzing works. We have unit testing, for example, and we have a sum function like receive A, receive B, sum, and return return the value. So, for example, 2, 2, 4, 3, 3, 6. Fuzzing is basically random inputs. Random, and we check if it crashes the system. So it runs 24 hours every day trying to find a bug. It's the idea. So it basically have a lot of random inputs trying to find a combination that can break the software. And for example, and Google OSS Fuzz runs a lot of open source projects infrastructure for fuzzing 24 hours every day for that. It's the idea. So and using fuzzing we can find a lot of bugs in the code. I suppose that most bugs we found in Bitcoin Core, it was fuzzing that found that. So
but the output of the fuzzer is it will be like the input for computing the block, or it actually is the input for different parts of the
Different part of the code is generally. So for example, I have a function that gets a transaction and tries to verify the transaction. Basically, this function we are gonna fuzzing. So we have other functions that do coin selection. For example, when you want to transact, you have to select the coins, and then we can try a lot of different combinations to see if it crashes or not. It's basically the idea, but it's related to the code by itself, different parts of the code.
As a developer, what's your opinion about Monero?
I generally don't like other cryptocurrencies. I don't study, and I think only Bitcoin is relevant because I have a lot of work to do. Monero is supposed to be private, but there's a lot of research that can realize that the privacy is not so good as we think. And I prefer some solutions on Bitcoin. For example, if you use Lightning Network, Bitcoin Lightning Network, you can have some privacy features. So I don't think it's necessary other coin with privacy features. We can have privacy on Bitcoin.
Nice to.
What about proof of stake? Like, what's the difference? What's the deal with that?
Proof of stake?
Stake.
Yeah. Basically, proof of stake is basically, let me think. So you have 5 coins, I have 5 coins, you have 5 coins, 5 coins, and basically when someone create a transaction or when we're gonna mine the block, the validation is according to the amount of coins that we had. So for example, if I control 100% of the coins, I am the owner of the network. This is the general idea, but the consensus of Bitcoin is proof of work, and there are other coins with proof of stake. Proof of work is basically a miner creates a block, right? And then we check the hash of the block. And for example, the hash of the block must start with 000. Then the miner checks the hash of the block and realizes, oh, this starts only with 10, for example. So what the miner does, he adds a number. So it's the content of the block, 1, check the hash. Oh no, 2, check the hash. 3, check the hash. So, but he does it millions per second to find a hash that satisfies the requirement. So this is a lot of machines that we know about proof of work. This is how proof of work works. And proof of stake is different. We don't have these machines. We don't have to calculate this hash this way. We basically want to have the validation of people that has coins. But there are other differences, but generally is the idea.
Other questions?
So if I'm not mistaken, Bitcoin started as a decentralized money thing,
Yeah.
right? Which will I think there was some discussion around it in the sense that it would not allow governments to take control of citizens and that kind of stuff. But it seems that nowadays Bitcoin is just another asset people buy to make some money, to speculation. Do you see things this way? Do you have any comment about it? How do you see the future of Bitcoin in that sense of? Because politics seems to be.
Yeah, some people has Bitcoin because they believe it's a freedom tool, and some people buy Bitcoin because they want to get richer. So each one has your own motivation, but there are a lot of people that believe that Bitcoin is a powerful tool, for example, for human rights, because no one can control your money, and you can take your money where you want, and that's it. But it depends on each person's view.
So you think that there is still room for that role of Bitcoin to be something important as a decentralized?
Yeah, true. Yeah, I believe.
All right, thank you very much, Bruno.
Thank you.
And see you all next year.